Okay, so hello everyone for this new edition of the GraceCon School, so GraceCon 2026. So here we'll have a big HPC school for 2 weeks now, and we'll start for the welcome for the direction of the laboratory. So Stefan will present that much better than me. So the lab, what we are doing, and why it's so nice to be in Annecy.
So welcome to everybody, to people which are in the LAPP auditorium and people which are on remote. So LAPP is an acronym for Laboratoire d'Annecy de Physique des Particules. And I will explain you what we are doing, focusing a bit on physics, but it will be quick. A bit of history. So the laboratory was created 50 years ago. Okay. Okay, so we stop for a few seconds because we are not displaying the screen. It's okay, they are changing. Okay, so I can restart. Okay. So sorry, there was a bit of technical issue for the start of this school. So as I said, the laboratory was created 50 years ago. And this year we are celebrating this anniversary. One of the reasons to be in Annecy is to be close to CERN, which is a center, the worldwide center of particle physics, so it's easy to go there. We are supported by CNRS, which is a national agency for research, and also for the University of Savoie-Mont-Blanc. We are here on the campus CNRS within the Annecy University campus. And we are also hosting another laboratory, which is called LAPP, which is a theoretical laboratory. Our research topics are ranging from large structures or in the observable universe to the most fundamental physics. So basically, we are doing particle physics, astroparticle, and cosmology. Just to show you that we are doing important things is that many of our activities are related to physics Nobel Prizes. You have the different dates. So we had in the past 5 activities related to Nobel Prizes. The most recent one is related to the discovery of gravitational waves. It's a collaboration between a LIGO interferometer in the US and the Virgo one in Italy. We had discovery related to the neutrino oscillation, to the Higgs boson prediction and discovery at CERN. And if we go a bit further in the past, in 2008, the Poisson symmetry, which is related to an experiment in the US. And almost 50 years ago, the first major discovery at CERN, which was WZ. And this is a small picture of all the experiments we are doing. So on the left, you have ATLAS and LHCb, which are at CERN. All physics which are related to neutrino, with the experiments ranging from Grenoble to the US, the Future Collider, which is called FCC at CERN. And now the 3 other topics are related to astroparticles. So we have finished to build the first observatory of CTA on the Canary Islands. We have the interferometer of Virgo. And the last one is a new telescope, which has started taking data in Chile. In our laboratory, we are involved on all the steps, starting from when we imagine the new detector, where we make the design, we construct it, we commission it, and we go to the operation phase, and we get results. A small picture of the world to show you all the experiments which we have worldwide. We have about the local teams, so we have 30 CNRS researchers, about 8 associate or full professor from the university, 15 postdoc, 15 PhD, and 60 engineers, technicians, and administrative teams. And we have roughly 20 software and computing people. About school and teaching, so a bit of display. So I have put a picture of the GraceCon school of 2 years ago. We have also, in 1 month from now, a school which is more related to physics, which is called GRASPA. And we had, beginning of this year, a school which is called Sustainable Scientific Software School. So this is really to optimize software, as you will do now, but on HPC. And if you have time for people in Annecy, you can visit our Utopia Discovery Center, which is just one layer above. About a few words about our computing platform, which we call MUST. So it's a computing center for the high energy physics data processing and storage, which is mainly related to LHC, which is a collider at CERN, 50 kilometers from here. We have a leading role in digital and R&D and also on the open science, including artificial intelligence. And we are open to university teaching, society, and the economy. And to give you an order of magnitude of the computing center, so we have roughly 7,500 cores. We have 21 GPU cards. We have 8 petabytes of data, and we have an external connection of 40 gigabits per second. I think at some point you will use this computing center to run your exercise. So to conclude, so people in Annecy, please enjoy the LAPP and the learning activities, and also enjoy the city. So on the left, you have the lake, which you will be able to see and maybe relax a bit when it will be hot. And on the right, you have a picture of the Festival d'Animation d'Annecy, which will occur this week. And in the evening, where it's dark, you can go to the Paquier and see some movies. Okay, thank you. Okay, so now we can really speak about the work of the conference.
Faire ça, parce que c'est une blague intéressante. Merci. Okay. 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 Don't have sound? Yeah. Ah. Okay. Okay, we have to wait a bit. Okay. It's okay? Okay. Okay, so now we will set the scene a bit to see what's going on during these 2 weeks. So first, for Grayscale 2026, you are a lot again, so more than 900 attendees on 59 countries. So that's the greatest school that we made until the first one. So that's quite an achievement. So 19 satellite sites over 12 countries also, and 1,200 people on Discord. So thanks to you, in fact, we do this school because of you. So you are here, so we continue to do the school, it's normal. So this started some years ago with, so you get the map here. So you that point here. So you have the France, you have the America, Oceania, so lots of people here. So we start everything with a Reprise project, which is a transverse project at Numpy 3, so the physics particle and nuclear physics of CNRS. So we are about 20, 30, depending on the year, but roughly we have 20 right now. And we are fond of C++, Rust, Fortran, Python. Everyone is following favorite language, and we are using also performance tools, so Valgrind, Perf, Macao, precision tool with CUDA, with Verificarlo, containers, Singularity Obtainer, Docker, Podman, Kubernetes, etc. And everyone is following his favorite technology, so SYCL, Cocos, HPX, Extensor, Vulkan, CUDA, HPC SDK, OpenVINO, OpenCL, OpenSCC, everything. And on CPU, GPU, FPGAs, we don't have FPGAs for this school because it's a bit too much, but we also have some people running on FPGAs, some stuff. And we started every time, as this school also, with simple example, because it's important to not reinvent the wheel, but know how the wheel works. So how to do an Adama product, how to optimize it well, how to do some reduction, some dot product, some matrix product. Of course, not difficult, but that's a starting point. And you have many libraries like MQL, like Eigen, like Armadillo, Ave, or Numpy and Numba to do this kind of stuff. But it's nice to know what's going on and how to deal with it. Of course, sometimes it's not enough, and that's why we introduce a new school, a new reaction in the school. So the Grayscale reaction, that's what we call it, the Grayscale school. And so you can see that as a chemistry game of life. So the idea is to have two species, U and V, and once you have enough V around you, V transform U in V, and then V use will become a non-interactive product, P, for the rest of the reaction. So we can define that with two couple differential equations. So they are really simple, in fact, here. So you get the Laplacian, you get the concentration of the product. And the point here is to have something really simple to understand, because it's just a couple differential equations. And it's really hard for the compiler to know what's going on and to optimize it well. So that's the main point of the school, so to use the worst possible computation to have the best performances at the end of the day, because of course we have a rate of really high speed up, as you will see during the school. It's really nice to have some intuition about what's going on, because you know big difference really quickly. So in terms of discretization, of course, it's continuous equation here, so we have to do a bit of work. So we have a Laplacian, and we will use a discrete Laplacian to discretize everything. So simple kernel for that to start with. So we have one cell at the middle, and then we get a stencil of neighbors around the cell. And we have some weight, and we do a weighted sum to do everything right now. So that's really simple. The goal is not to compute really complex stuff. It's just to understand how does it work. So you have the neighbor heuristic, which is really nightmare for the compiler to understand and for the CPU to optimize as well. And then we can vectorize. So we vectorize or we GPUify. And then we have the data layout, which is really complex, and we have to deal with really nice way. The compiler, we have to ask the compiler, okay, we have to use certain options to do some stuff. We have to give some hint to the compiler to be sure that everything is nice, and a lot of stuff also, but we will see that during the 2 weeks. We will not spoil everything right now. So in terms of languages for 2026, we will have C++, Fortran, and Python. So Adrien does not have them this year, so no Rust. At least in main lecture. We'll have a bit of Rust, of course, but not in main lecture because we don't have time. But after we'll get that also. CPU with NUMA. If you don't know what is NUMA, don't worry, we'll explain that after the presentation. So C++ with TBB and with Eve and Cocos. Fortran with TBB also, and Python with Numpy and Numba for the first week. And then for the second week, we will have, for the GPU, CUDA and Rust, the HPC SDK and the Cocos for C++, Fortran with the HPC SDK and the NV Fortran with all the magic that come with it, and cunumerics and legate for Python, and JAX also. So in terms of tools, we use a lot of tools, in fact. So for performance perf, we get perf, we get Macao, we have Insight, Valgrind, and also VTune and other stuff, as you will see tomorrow with Sebastian, other extra lecture about that. And memory profiler, because it's really important also to know what's going on in memory. So Malt and NumaProf, we'll have also a lecture dedicated to that. Compiler, so we use LLVM and GNU, of course, and NVIDIA and Intel compiler, depending on what we want to do. It's important to have a large panel of what's possible to do. And then for precision, CADNA and Git, GitLab, CMake, classical stuff to build a project and to version project. So at some point, we start the first school and people from Teractech get to see us and say, oh, it's nice to do a school with 30 people, but what about 200? Okay, you are 900, they fail again, but but come on. So Teractech, it's an association, and the goal is to do some valorization, dissemination of knowledge to make schools and seminars and interview, and the goal is to really make a bridge between the academy and the industry world. And they are the French antenna of EuroCC, so a catalog of formation for HPC, HTC, HPDA, AI, quantum computing around other countries in Europe. And it's the formation part of EuroHPC, so you might already know if you know Surf, if you know Cineca, if you know Leonardo, all this kind of really big computing center, Jupiter and or TGCC, this kind of stuff. So they are all funded by EuroHPC at the end. So we have a multi-site diffusion for this school, which is really hard to make work, but it's working. So the main site is Annecy here, with all the people, all the teacher, with about 40 people, so including the teacher, so you are a bit less than 30 here in terms of attendees. So we have all the laboratory involved in this school, all the teachers, and we stream live on YouTube and on Discord. So you have to go on Discord, of course, to get all the information. And a bootstrap day at the end of the 2 weeks, so you can go with your problem, with your question, and we will do our best the last day to help you on everything you want, any topic you want. So then we have 19 satellite sites, so from in France, in Europe, in the whole world, in fact. Thanks to all the satellite sites to play this game and to support us also for this school, because it's also, of course, it's hard to organize, and some satellite sites are present every time since the very beginning, so it's really nice of them to be here. We are also sponsors, so that's why you have a free meal every day at lunch. The night we prefer to let you do what you want, if you want to go downtown to see the festival animation or stuff like this. But all the days at lunchtime, everything is offered. Of course, it's a free school. So thanks to CodeRecon and Do It Now, so the two sponsors for this edition. And as Stéphane said before, you will use Must if you want for this school. So here to use some GPU mainly, because for CPU you can also, if you want to check some stuff with NUMA, this kind of stuff, but we'll see that later. So this is the computing center of LAPP. And we have extra services also. So if you jump on the Jupyter Hub, so you will see this URL here. You will get here to Grayscale 2036. You have a couple of lectures here also if you want to play directly from your favorite browser. So you can jump here and see what's going on. So we'll not dive into much detail today. We'll see that tomorrow and the day after. But you have lots of material for that. And also, yeah, we use Condor. HT Condor are not classical Slurm as many computing centers. So we have normally, you have everything to use htconda in your home in the lecture, in the formation directory, so normally you will not get lost, and we'll see that tomorrow, but normally everything should be okay. And finally, some URLs, so if you want to have the timetables, I have the container of the MUST formation platform, introduction to MUST, this kind of stuff. And also I have to mention that go on Discord and you will have everything. So you have the satellite site, you have all the lecture will have you here. So you have the live, you have the question to teacher, you have normally all the lecture here. For all the lecture, we have a channel. So if you have question related to one channel, you can go here and ask your question. And maybe I can show you to finish program, not you. I have too much. Not you. Okay, so here you get in your website, and then I jump here. I get to here. So this first day will be practically mainly theoretical. So the idea is to explain everything, at least for the CPU part. We'll see the GPU theory next week. Then C++ Magic, Fortran, Cocos with C++ and Python. And at the end of all day, we have a dedicated seminar. So unit testing, profiling tools, memory profiling, computation and precision, impact of the operating system on your performances, because you will see that the performances are huge. After the school here, we will have a welcome tartiflette, which is important to have a social dinner, so it's a social tartiflette. And for people here in Annecy, we will have a visit of the LAPP museum also on Wednesday during the lunch break, just after the lunch break. And then little shifted hands-on with Sébastien. You will enjoy, I assume you will enjoy it on Saturday morning, and then question to teacher. So not a bootstrap, but kind of discussion. So this will not be streamed. So we are free to talk about everything and as we want. So no problem with that. When you will be free on this day, you can have a normal weekend. And then the week after, so we finish with Eve on Kiwaku on the CPU part. So how to deal with vectorization, with data organization, stuff like this. And then GPU Blackmagic and GPU with MVC++, with CUDA, with Rust. And then Python on GPU, Fortran on GPU, Cocos on GPU. And then a little webinar on Julia, but not the one you are thinking of. And part about how to optimize cubic root with Vincent, and then a presentation of what's next, because there is a plan. So we'll have all the information at this moment, and then the bootstrap. So you are free to leave when you want for the bootstrap. If you want to stay the whole day, you can, of course, no problem. And if nobody has question, I'm pretty sure that we'll move on with Sébastien on the CPU architecture. Okay.
VM qui a rebooté. Come on. Should not do slides on Windows. Okay, we wait a few minutes or it's okay. So welcome to the CPU weeks. So this week we will speak only about the CPU, not too much about the GPU. So before speaking about the CPU, we need to know what is a CPU. Okay, so welcome to the CPU architecture course. So first I want to give a special thanks to Adrien Grassland, who was making this course the past years. And part of the slides are just a refresh of his presentation. So thanks to him for the basement of the support. So before speaking about architecture, we need to know what is an architecture. So in computer science, we can speak about two things. First, the ISA, the instruction set architecture, which you probably know under the name of x86, ARM, or RISC, or x86-64. I will not speak about that part of the architecture world. We will go a little bit down on what we call the microarchitecture. So how the processor is built, because this is what we will need to understand to get the performance and to extract the best performance from the CPU. So the microarchitecture, this is the internal details of the hardware, which is not well known. The founder of, the CPU builders, they don't give us all the key to understand everything on this part. So we have to guess a bit what they did. But there is some common points which we can base on to make our optimizations. And this is what we will try to understand here. Notice that the microarchitecture is evolving over time. So let's say every 2, 3, 4 years, you have to update yourself about where this world is, because it is changing quite quickly. So let's say that there is some common part which can be taken into account quite easily. So there is a subtlety here. Your code needs to take into account the microarchitecture to get the performance. But as the microarchitecture is changing, and not the same depending on the hardware provider, you need to be not too tightly dependent on this architecture. So you have a kind of balance to do. I mean, be dependent on it, but not too much. This will be a kind of game to play. And the goal is that at some point, your code should be portable over as many architectures as possible. So you need to try to find the common points between all the architecture which are available to try to optimize your code. So let's start with the common view, how a CPU is built. So if you have a CPU, the most simple CPU you can do, you need to put some component inside. So an arithmetic logical unit to make the computation, to make the addition, subtraction, etc. You need a memory because you need to compute on some data, of course. So the memory is outside of the CPU, but it is there. At some point, we have to take it in account in the pipeline. You have an instruction decoder because you need to decode the instructions. And as a bare minimum, some registers and some memory transfer components to transfer the data from the memory to the registers. Okay. Of course, in a real CPU, there is more component inside. I will not list all of them. This is not the goal here, not in half an hour. But we'll stick with this view of what is a CPU. And we'll see already what we can do with that. The I/O part to access the hard drive, GPU, etc. We will not discuss it here. We will focus only on the computing part, okay, to simplify a bit the view. So let's take a first basic execution. For example, if you want to make a simple addition, you need to load the data from the memory, transfer it to the registers, and then make the operation in the ALU. Store it again in the register and storing again in the memory. Okay, a very simple step. Already you need to think that in hardware they have to cable everything. This is not so easy for the hardware provider to build all this hierarchy of components. And we can split in practice those instructions in something we call a micro-op. So every operation on the CPU is splitted in micro operations, which is in practice when you want to make a load, you need to fetch the instruction, fetch the load instruction in the CPU, to decode this instruction, to interpret what it is, what it should do, probably load some data in a register, or from the register, sorry, make the operation, the addition, the subtraction, the if branches, etc., and store again the data in the register after you have make the operation. And you chain your micro-op like this. Every operation has a few micro-op to do: fetch, decode, load, operate, store data, and again, for the last operation, I do again the micro-ops. Okay. Here, if I'm a processor builder, I have some things I want to optimize. I want to optimize the time I pass in every micro-ops. This is the goal of Intel and AMD, to make the micro-ops the fastest as possible. So at some point, you might reach the point where a micro-op is one cycle. So you can go faster, or you need to increase the frequency of the CPU. But here we will speak about the architecture part. In terms of architecture, we cannot do more than one cycle to make an instruction, a micro-op. For the operation part, depending on if you are working on floating points, integers, etc., this will take more time or less time depending on the operation you are doing. So at some point, you will have to optimize. I mean, the founder of the processors have to optimize these numbers. And for every generation of processors, you can see that those numbers are decreasing. So the processor is faster even by not increasing the frequency. But at some point, you reach the limit. You cannot go as fast as possible. There is some theoretical limit on what you can do. And again, if you reach one cycle, you cannot optimize anymore. So what we can do? We can do one thing. First, you have seen that here, for one operation, I pass many operations to just handle the instruction I have to execute. So I can say one first thing is, can I give more job to one instruction? So if I divide the jobs done by the size of the instruction, I get statistically more work done. This is what we call vectorization. We will try to give more work to one instruction. So when we are summing some arrays, this is something we are doing quite oftenly in computer science, looping over an array and making some operation on every cell. We can do either one by one and with one instruction for every cell, which costs a lot, and because each time I need to decode, fetch, decode, fetch, decode, fetch, decode, fetch, and execute the instruction. Or I can do the vectorization. Vectorization is to say that I will take not one instruction, one element per one element, but this time, for example, 4 elements by 4. So I take 4 elements, I make the sum for the 4 elements in one go, in one instruction. So I pay the decoding only once for 4 instructions. So I gain a bit of speed up like this. So I will not discuss too much about this vectorization, because the next course will be speaking about it a bit more in depth. But let's say that for the vectorization, there is 2 ways to do it. Either you explicitly explain to your code how to vectorize, or you let the compiler do it for you. Okay. Ideally, it's simpler if the compiler is doing it for you. But we will see this week, this is not always so simple. So sometimes we have to use some special instruction sets or frameworks to do the vectorization. for example, Eve will be one of the one we will discuss this week. So I will not enter more in details in the vectorization here, because Vincent will tell you more about this. Now we will focus on one thing, which is the key improvement of the modern processors is the concurrency and parallelism, which are inside the processor itself. So let's say we take again the operation we have seen before, making a load, an addition, and a store again to store the data in the memory. If I do it naively on a simple processor, I will just do fetching the instruction, decoding the load, loading the data from the register to the internals of the CPU, making the loading, storing the data, and fetching for the instruction add, and same, executing the instruction add, and making everything for the store at the end. Okay? Let's say it takes, for example, 15 cycles if I consider that one micro-op is one cycle. I simplify a bit because it's not the case in real life, but let's say this is it. The processor builders has made something which is called the pipelining. I want to make those operations in parallel because when I fetch the first instruction, when I'm decoding the first one, I can also fetch the second instruction in parallel because my fetch, the unit of the CPU which is responsible of the fetch is free to work. So I can make a working chain like this by putting all the instructions in parallel. This is what we call a pipeline. Okay, this is like the Ford mechanism. When we built the cars in a few years ago, we started to make this kind of chain to build the car. Every person on the chain is making one thing, and we can make those things in parallel. And having several cars in parallel in the pipeline, everyone at a different stage. Okay. So this is interesting because already we can gain a bit of performance because now instead of having 15 cycles to execute, we pass to 7 cycles. Okay. Here I have only 3 instructions, but in practice, as my pipeline is how many? 1, 2, 3, 4, 5. I can have 5 instructions in parallel in flight in the pipeline at the same time. Okay, so I can gain even a bit more if I have more instructions to execute. So the ideal scenario is that you have n instruction in flight in the pipeline, so you get a factor n of speed up in terms of execution. Here I have represented a pipeline of 5 stages. In practice, in a real processor, this is more 10 to 20 the size of the pipeline you have in your Intel or AMD processors. Now, with the pipeline, there is a small problem: is that, of course, your program is not a list of instructions which are independent one of the others. You have some dependency in your program. For example, let's say this example with an if statement. When I execute the if statement, I cannot start to execute the next instruction because I don't know if I should do A++ or A-. Okay. So how the CPU is handling that? It executes the if statement, so start it in the pipeline. And what I can do is to make speculative execution. I can say, I guess that I will take the left part of the if branch and execute the A++. I speculate. And I launch that on the CPU, and the CPU is starting to execute the A++. But what can arise, of course, is that during the execution of the if statement, here I understand that I'm going to the right part of the if branch and not on the left one, which means that I need to consider this operation not done, and I stall the processor, I block the pipeline, I flush the pipeline, so cancel all the operations which were running and which were virtual, kind of, speculative, and I start again the good operation, which is the A-. Okay? So our goal when we will optimize a loop or a program is to give as most parallelism as possible to the CPU, so it didn't stall in its pipeline. Okay, because every time we will stall, we will lose some execution time, and we see that here I'm kind of not parallel at all in terms of execution of my instructions because my program is too dependent. So I can give a small example. So if ever you want to play, all the lecture I will do, we'll use the memory Docker image, which is available on the list table on the website of the school. So there is some micro benchmark inside the directory. There is a directory 2 CPU architecture and one benchmark which is called one branch. If ever you want to execute yourself on your side, I will make the demo at the end if I have time, so we can look at it. I make a simple loop here, so a for loop with an if branch, depending on the data which is inside the buffer. If the buffer is below 127, I make plus plus. Otherwise, I make minus minus. And I can make two executions. I fill my buffer with some random values, which means that sometimes the if statement is going one way and sometimes the other way. So the speculative execution cannot guess what it is doing. And if it cannot guess, I get 3 cycles per iteration for performance. Yeah? Is there a microphone for... yeah.
Is this without unrolling? Or is this,
Sorry, ask again?
Is this with unrolling or without unrolling? So do you unroll and you just do O3 and no unrolling?
This is O3.
Yeah, but like if you look at assembly, is it any unrolling? Like I'm just curious about the random.
You can have the unrolling, but in any way, the if statement will cost 2 or 3 times more because you cannot predict what to execute next. So in the random case, you will speculative execute one of the branch, and half of the time you will be wrong.
Yeah.
So at least you get a penalty of a factor 2, and in practice, to stall the pipeline will cost you a bit more than a factor 2.
Mm.
So this is why here on this is on my laptop, I have a factor 3. Yes, the other case is uniform. I put only zeros on the buffer, which means that all the time I'm taking the same if branch. So you see that already, depending on your case, the branch predictor can be missed or not. So this will be also something to optimize probably in your code, depending on what you're doing. So the next step, we have said was that we have the pipelining. So if I execute with some units, I have a load unit, a store unit, and an ALU. I can schedule my operations. If I have this list of operations here, I have 2 variables, A, B, and D, and E. And I need to make many loads and many store, probably. I can schedule those operations like this. And because I have only one unit to make one operation at a time, I need to make one load for one cycle and the next load to the next cycle. I cannot parallelize the loads at the same time. Okay? So in my CPU, I can make one improvement, is to put, instead of having, so it's taking 7 cycles like this, if I am making the optimized execution with pipelining. And now I can say, instead of having one load unit in my CPU, I can put 2. Okay, so now I can load two variables at the same time on my CPU. And this is what most of the CPU are doing. You can make 2 to 4 or 5 loads at the same time. Same for the store, same for the executions, etc. Okay, so you have several computing units for every kind of operation on your CPU. A limited number, of course, which is just a few. But you can win a bit of parallelism like this on the CPU. And now it's 5 cycles instead of 7. Okay, it's not perfect. I didn't win a factor 2 because I doubled the number of units, but I win a bit on this simple execution. So this is something also when you will have to optimize some loops for a specific architecture. If you want to target a specific architecture, you will have to take into account this kind of numbers if you target a specific architecture. So let's give an example. For example, here I wrote, just to be able to use the different units, you need to have no dependency between the operation, of course. This is some operation which can be executed in parallel because they are not dependent one to the other. So I can write 2 kinds of line here. I make the same operation, but grouping the operations. So either by putting some parentheses for every member, saying UI plus 1 plus UI plus 2 with some parentheses. So every time I'm forced to make them one by one in order. Or on the right, I make them by groups. So I kind of express some parallelism in terms of how my operations are, my line is written. And you can see on this example here, which is a bit a forced example to show this case, that if I'm executing the operation per group, I have a faster execution, okay? Because I'm using in a better way the pipelining and the multiple units I have on my CPU. You have exactly the same kind of problem if you make some indirections. If you put some indirections, because you need to wait to have the previous indirections done to execute the next one, you lose some performance because the CPU cannot execute many things in parallel. So we can say, why not putting 1,000 of each unit on the CPU? This can be something we could have done. But the problem is that in practice, one program, a single program, does not expose enough parallelism for this inside this single thread execution. Because in a program, most of the time, you finish with an if branch, with some operation which depend on the others. Of course, when you manipulate a variable, it's to use it 2 lines later, and not to use it 1,000 lines later, most of the time. So in practice, the dependency chain in your program did not allow the CPU provider to put a large number of units, which limit in practice them to a few. 1, 2, 3, 4, 5. This is the most you will have on most CPUs. So how to make better? You can say, I have not enough parallelism in one program because of how the programs are statistically. So why not executing 2 programs on the same units? Okay, I can. This is what we call SMT, symmetric multiprocessor multi-threading. So hyper-threading for the Intel name. So here the goal is we share the load and store unit with 2 threads. We have 2 execution units on the same core. And those 2 execution units will execute 2 programs differently with the same computing units. So they are shared. So the good point is that if you have enough parallelism with the 2 programs, you will fill the units as most as possible. The problem is if one program is saturating one of the units, the other program is slowed down. Okay? So hyperthreading, you will see that in practice is very hard to use in practice. For example, if you mix one program which is doing a lot of floating point operation with another one doing most of the time floating point operation also, they will kind of fight for the shared units. So it's not good. If you mix one program making integers and one program making floats, it's good because the units are shared and they are not conflicting for both. So you can say we can make better, of course, which is not sharing the units. So we make what we call cores or multiple processors on the same machine. This is how it has been done historically the first way. You say for every core, you have a scheduler and all the units dedicated to this core. Okay? And then up to you to execute either several programs on your machine, 1 per core, either to make some parallelism inside your program with threads. Okay? The threads, you will have to handle by hand in threads that you are sharing some data because of the execution. Everyone is okay with what is a thread, what is a process? So a process is executing one thread, for example, and have a unique memory, which is not shared with the other processes. I should have put a picture probably. We'll discuss that again at the end of the week, but I can explain now. A process has a unique memory shared with all the cores, with the program, where when you have several threads, they share the same memory. So they are attacking the same data. Okay? It's efficient in terms of programming, but then up to you to make that the different access to the same data is not made the wrong way with mutex and logs. Of course, you can make a mix. You can say you have cores, and you make some SMT, some hyperthreading inside the cores. And if you are looking, most of the CPU you have on your laptop, this is how it is designed now, today. Okay? Hyper-threading inside the core and multiple core in your CPU. For the number of cores on your laptop, most of the time you have 4, 8 cores, something like this. Even more on some laptops which are a bit powerful. And on a server, on a large server, you can have up to 64 cores on the same processor. Okay, then you have to express a lot of parallelism and to handle it by hand, by yourself. We'll see this week that this will not be so easy. And for this, we need some frameworks or some help to program this. So just a small summary of what we have seen up to now about the kind of parallelism inside the processor. We first have seen the pipelining, which can give you a speed up of 10 to 20, which is fixed. This is what the hardware provider has decided to do. You cannot play with that too much. And in practice, you have to rely on what they did on their side. For the tuning part, you cannot do too much, a bit in your code to exploit it in a better way. But the optimization you can do for that is a bit limited. For the SIMD, so the vectorization, you can have some vectors up to 8 or 16, depending on the number on the processors you have. If you have a recent one, it can go up to 16 for 8-bit elements. This is quite easy to optimize for a small code, which is simple. But when your code starts to become a bit complex, you will see quickly that making a vectorized version of your code is not something very easy. So it requires some hard work to get it in practice in real life. We have seen the superscalar part, which is executing many instructions at the same time with multiple units in parallel in the CPU. Again, this is forced by the compiler. You can speed up the CPU by a factor 2 or 8. Again, this is an hardware constraint, so you cannot do too much things by yourself on this. But the CPU is faster thanks to this part of the implementation. To use is quite easy. Huh? You let your compiler making the work, and in practice, it's going quite well. SMT for the hyperthreading, you can get a speed up of a factor 2 at best, because you have 2 hyperthreads on one CPU, on one core. In practice, to get the factor 2 is very hard. You will see that most of the time, if you get a factor 1.5, it's already very good. 1.2 is more what you get most of the time on this. And then the multi-core programming, as you can get up to 64 or 2000 core on one machine with 2 processors, you can get a speed up of a factor 200. So this is probably where nowadays we have the more gain in practice in terms of performance, is to make your program parallel. If you want to exploit the architecture of today, you need to have a program which is parallel. So there is many ways to do it. We will see this week many frameworks to do that. This is not the easier part to introduce in a program which is already existing, but in a new one, you can think it from the beginning to be parallel from the start, and it's quite well in practice to get the performance. So up to now, we speak about the processor in terms of computing. So I think you have all this view. I summarize. You have the cores, the hyperthreads inside, some superscalar, so parallelism in terms of instruction inside these cores, and some view like this. And now we need to add one component to the performance when you are making a program, of course, is to access the memory in terms of data. Because computing without having some data is useless. Of course, you need to store and access some data to make something. So let's say we have a simple view. You have the computing part of your CPU and some memory. This was the very beginning of the computer science, some very simple processors. Of course, we add quickly some registers. We fetch one element from the memory, we store it in a register, and the register is very fast. So we can compute it, we can compute on it very fastly. We say we make some parallelism. So if we make some parallelism that way, we will have several cores accessing the memory, which will quickly be a problem. Because if I'm taking an AMD EPIC, a recent AMD EPIC processor, we will have 64 core, for example, on this machine. 64 core, which is running at 2 gigahertz. We can do 2 FMA. FMA, this is float multiply addition. So this is making an addition and a multiplication at the same time in one instruction. Okay, so I can manage two operations in one cycle. If I'm using some vectorization, etc., it makes that I'm doing 16 operations per FMA. If I count in total, it makes that I can do 4 multiplied by 10 at the power of 12 floating point operation per second. That's a huge number, very fast. I'm happy, I have a fast processor. Yeah, but now I have to access some data because I never compute on nothing. So I need, every time I make a computing, sometimes I need to get a data, compute it, store the data, take the next data, compute it. And in practice, I'm all the time exchanging some data from the memory, not only computing, depending on my case. If I'm looking on the memory side, on a processor, so if on a server with 2 AMD like this, which you fill with all the banks you need to fill about the memory to have as much as possible, you can get a bandwidth of roughly 0.05 floating point operation multiplied by 10, so power of 12, so the same than on the right, which means that your memory is 80 times slower than your CPU. Okay? So you quickly see the problem is that if you build an architecture like this, no way to use a 64-core processor. You can use a 1-core processor and it's fine. The other cores are just waiting for the data and making nothing. Okay, it's a bit like you. If you go to the supermarket and you pass 1 hour to go to the supermarket every time you want to make your cooking, you will not cook a lot. For making an example of the real life. So how to proceed? This is what we call the memory wall in practice. This problem. This is quite old. And it's becoming worse and worse, kind of, because the speed of the memory is not accelerating as fast as the speed of the processors. And you know the processors is kind of following up to now, because now we are a bit not following it anymore, the Moore's law, which is exponential. But it's exponential also for the memory, but not at the same speed than for the processor. So the gap between the two is increasing, which means that if you don't take care of how you optimize your memory accesses in your program, you will be stuck. So how to solve the problem? We say we have compute, registers, the memory. If I'm going to the supermarket to take my vegetables to make my cooking, I can take the vegetables one by one, or I can take a lot of vegetables, store it in my home, and making my cooking on all of the data, and making the going back to the supermarket only sometimes. So I can either increase the bandwidth with the memory, which is not possible at some points because I cannot put as many links as I want, or I can put a cache, some local memory storage inside the processor. So I can copy part of my data inside this cache. This cache is faster, so I can access it very fast. And when I need the data from the memory, I put the data from the cache to the memory, take another one, and work fastly on this memory, etc. Okay? So this is what we call the L1 cache, level 1 cache today. So there is two level 1 cache in practice in your CPU today, one for the data and one for the instruction. So they don't fight each other, depending on what you are doing. The L1 cache is roughly 32 kilobytes on most processors you have today. If you take the one you have on your laptop, it's roughly the size you should have for the L1 cache, which is quite small, because when you have how much you have on your laptop, probably 16 gigabytes of memory for most of you. 32 kilobytes, this is quite small in compared. So you can add a second cache level, an L2 cache, which is larger. But in terms of memory, if you make a memory larger, it's most of the time also slower. Okay? So you put an L1 cache, which is small and fast, an L2 cache, which is a bit bigger but a bit slower. And you can also put an L3 cache, again, a bit bigger and a bit slower. So in terms of size, most of the processors, you have this kind of size, 32 kilobytes for the L1. For the L2 and the L3, it depends on the version you have of the CPU. The order of magnitude is 1 megabyte for the L2, 256 kilobytes most of the time, depending on what you have, and 24 megabytes for the L3. Depend on your CPU, of course. If it's an HPC CPU or a laptop CPU, the number is changing. Anyway, you have this cache hierarchy, which means that if you are accessing your data without reusing it anyway, so you mean you access one data and use it only once, you will not use your cache because you fetch the data in your cache, you use it once, and return it to the memory. Okay, so we'll see tomorrow an example about this on the Grayscale simulation. We need to take in account the caches if we want to have the performance on the CPU. Of course, it's a bit more complex in the real life, because in the real life, we have said that we have cores on the machine. So if you have many cores, sorry, I didn't put some box around it. So you have one core here, the first core with a compute unix, the register, and the L1 cache. The L1 cache is most of the time local to one core. Each core has its own L1 cache. Then you have a second core in bottom here, which also have its own L1 cache, and then the L2 is probably shared between both of the cores. And the L3 is also shared between all the cores you have on your CPU. So if you want to take an example on your machine, you have the hwlog command, lstopo, which permits you to display the hierarchy of cache of your CPU. So it can display like this in text, or you can get a picture. So this is a real processor, a very simple one. This is an old one here, probably the one of my laptop, with 4 cores. So you can say that you have a core, you have the hyperthreads, which are here, the 2 threads which can execute on the same core, the L1 cache, which is private to the core, the L2 cache here, which is private to the core, and the L3 cache, which is shared between the 4 cores. Okay, so we see that there is a hierarchy of cache in the machine. If you want, of course, to optimize your program for this kind of machine, if you are using more than 32 kilobytes of data, you will have to take in account this cache hierarchy if you want to be optimized. On some laptop, we will discuss this more at the end of the week. You can have some processors like this, a bit more complex and a bit less symmetric, because here we see that we have some fast core with hyperthreading and some kind of low power core with no hyperthreading. This is what you can find on some laptop. Probably some of you have this kind of CPU. This is a Core i9 at Intel, which has some slow cores and some fast core, and depending on if you are running on your battery or not, it's using more the one or the others. And on a HPC cluster, you have something more symmetric most of the time. Here it's an HPC cluster with two processors. Each processor has its own L3 cache, and inside you have the cache hierarchy as usual, L2, L1, and the core, and you have here 24 cores per CPU. Okay. So at some point, when you are making a program, if you want to be very optimized, you need to take into account this cache hierarchy and this hierarchy of memory. So we'll discuss all this memory stuff on some of my courses. So a bit tomorrow and at the end of the week about how it is running in terms of caches. I don't know what time it is. I'm a bit in advance probably, so I will have time to run the examples. If you want some materials, I put some links here. I will share the slides on the school website. We need to upload it. There is some materials. If you want to know exactly all the details about your CPU processor, if it's an Intel one, you can go to ARC, which is one of the websites of Intel where you have all the details, number of cycles it takes for many things, the cache hierarchy, the number of units, etc. You have everything. Same on AMD, you can look on the documentation. And there is some people also, Agner, this is the one who is, every time there is one processor which is going out, he is measuring the cost of every kind of instruction on the architecture to see how the architecture has evolved. Because of course, in the documentation, Intel as AMD is not telling you everything about what they did. So some people are kind of, every time there is a processor going out, kind of measuring what the builders has done to try to understand how the new architecture is done. So Agner is one of them here. You can go on his website to get many things. I will stop here for the theoretical part. I don't know, I'm 10 minutes late. I can just maybe launch the two programs. So if you go in the virtual machine, maybe Pierre, I should make an example, no, how to. For the people here, if you go to the Jupyter Hub station, you can access. I will stop my server, so I will not have one. You can access your machine, the containers here for the people at LAPP. You can access the Jupyter Hub platform and select. The problem is that I already run it, and I blocked. Yeah, mine is already running. Select if you don't yet run it, you have the Grace Code 2006 element, and select the memory container in the page. So you will land here, where you will have all the things we will discuss all this week about memory, and you can go to, maybe I can zoom. You can go to 2 CPU architecture, and we can execute the benchmark, which is branch, DevOps. So this is the program I have shown you during the presentation, and just to execute it on your eyes. So I can compile everything, already done for me. So the branch execution, which I was saying before, so the case with the random values in the buffer. I'm executing. Here I have 6 cycles with the random part and 3 cycles with the uniform part. Okay, this is exactly the plot I have shown you before. I can run the depth chain. Again, depending on the way I grouped the floating point operations to make a dependency chain or not, I get a different execution time, which is here 2.55 cycles against 1.8. So you see there is a gap depending on how I organize my line to make the same operations. It's just that I pack them in another way. And sorry, this one I maybe make a mistake, so I will just execute it with OMP num threads equal 8, not to saturate too much the memory of for the caches. Sec. Here it's an example to access the various levels of memory. I made an example to access different levels of memory in the cache. So either to compute in the L1 cache, either to compute in the L2 cache, the L3 cache, or the memory. And I'm just operating on an array in terms of loop and using it many times. And if I'm in the L1, it's 1.5 cycles to make the computation in sequential. So I'm running only one thread. With the L2, 3 cycles. Already, this is kind of 2 times slower if I'm running on a larger data set. On the L3, here I'm a bit faster, so I don't know why. And in the RAM, 4 cycles. But here I'm running sequential. You know that the CPU now has a lot of bandwidth because it is there to feed all the cores of the machine. So if I'm running in parallel, let's say it's run OMP. OMP, we see that already in OMP, the RAM, because it's not capable of feeding all the cores as fast as possible. When I am accessing to the RAM, I'm a bit slower. Now it's 11 cycles to access one element for one thread. Okay? So when I'm using all the cores of the machine, all the threads are 12 times slower than if I'm using the L1 cache. Okay, so you see that if you are in the cache, you will be faster in your programs than if you are not. And I will stop here and give the hand to to the next part. Ouais. Il y a eu des questions sur Discord? Ouais, je réponds. I will answer to the Discord questions offline. Any question here? Everything is clear? You are nice with CPU architecture. Ready to optimize everything. Thanks.
Hello, everybody.
Just a remark about the CPU. There was a lot of questions about how the cache decides what to evict and what to keep, who is making the allocation. We will discuss that on Friday about the operating system impact on memory management. So we'll discuss in more details all these cache hierarchy behaviors.
So I'm Vincent Lafage, and I will tell you about parallel programming. And in our case, we want non-Euclidean programming, because if it were really parallel, we would never have all the threads meeting together. It could be some problem. So we have seen things from the side of the CPU, from the side of the hardware. A bit of motivation for this. Most of you are already probably aware. We have been educated in the Moore's law. It started with Gordon Moore's observation in this paper in '65. With only 6 years of data, and the number of transistors was already doubling almost yearly. So about every 2 years, even before a microprocessor existed. So as you know, it continued over the last 50 years. And at first, there was some obvious usage for this. We wanted more register, more memory, more cache, more processor instruction. We wanted to extend the bus size. We started with 4 bits only in '74. And we are now at 64 bits on every desktop in every pocket. In the early 90s, end of the 80s, we started to have memory management unit, which allowed for what we consider for granted in our OS operating systems. We have also extended the number of processing units, because even with only 1 core, we could have, at the end of the 90s, many arithmetic and logical units, as well as many floating point units. So there was, at that time, a bit of contest with AMD that had 3 FPU, and Intel had 2.5 FPU, and you could, looking at the execution of the same program on the 2 CPU, see this factor 5, 6 operating. We used it to have more pipeline depth. You have been told about superscalar architecture. So it started with the Pentium around 93. And afterwards, as you have been told, there are also very complex branch predictor. If you look at the die, almost a very significant proportion on the surface is dedicated to this branch predictor. But we have many curves to look on this diagram. If the number of transistors steadily rose, the single thread performance started to top in 2004. And the frequency also started because of the so-called power wall, heat wall. The power dissipated by your chip goes with the frequency. So at some point, you have to stop. So this power wall introduced a frequency wall that you can see. It has been 20 years that the free lunch is over. We cannot wait for the next generation of CPU to increase the speed of our program. We have to do something. When you look at the size, you also realize that even if there is much hype under the name the 1.4 nanometer of the Intel roadmap does not relate to the same size as the 10 micrometer that was really physical size. At some point, we'll have a tunnel effect, so we have also a quantum wall. On the wall that will make all this Morlow stop at some point is the money wall, because the factory that will build this chip cost really billions of dollars. So about the frequency on power wall, if we had continued along the same way, by now we would have something as hot as the sun surface on our lap, which is not very safe, to say the least. Some other problem come on top of this, because you have noticed that the energy is not cheap and is not cheaper. A computing center, a national computing center, but a small one, would have to pay something of about 1 million euro per year only in energy. This energy is rare, expensive, and sometimes also dirty in different way. And we already have moved to exascale. So you expect the number of operations to go with the power. Hopefully, the Comey's law stated up to 2010 tell us that we make much more computation per kilowatt hour when time increase, doubling the efficiency about every 1.57 years. This was true until 15 years ago. It is no more the case, but it depends very much on the constructor. This led in the 2010s to things that led to ARM architecture. So we may want slower chip with many more cores. But we have to exploit the parallelism. And as Sébastien just told you, the increase in the CPU power has not been matched by the increase of RAM speed. So now we have to do something like 80, 100 CPU operation to take the more of what we want. Some motivation for this, and if people from electronics are in the room, please don't be too harsh. It's a very crude modelization of memory. We want to store some tension in this capacitor. We have to push electron in the wire. And so we have a trade-off, because we can wait for a longer response time of the order of the latency, or push more current. If we push more current, we will dissipate more energy. And so the physics says communication is slow, power hungry, or both. So a lot of, we have to settle on some intermediate. It leads to a hierarchy of memory, small amounts of fast memory close to the CPU, and large amount of slow memory far from CPU. So as you have just seen, you have CPU registers that are faster, but smaller than level 1 cache, and in turn, level 2, level 3 main memory, the disk, and even the internet is a very slow but very big memory. So we must feed the CPU, and it means some problem will be memory bound. And we need to think about the kind of problem where we will be memory bound. The proper quantity to look at is the so-called arithmetic intensity. So if you have a problem of size n, a vector of size n, a matrix of size n, if you want to do a dot product of two vectors of size n, you will move n data. you have n multiplication, n addition. In the end, as many data movement as operation. If you do a convolution, it's a dot product in reverse. Matrix vector product, you move more data because the matrix is bigger, but the number of operations doesn't change. But if you move to matrix-matrix product, then you move two matrices, 2n square data, and you take n cube operation. And here, you can benefit from the power of your CPU. You have, for a large problem, many more operations that you have data movement. So, is it only dense matrix? No, of course. What is using dense matrix product, matrix decomposition, factorization, reduction for system inversion, diagonalization, and a Fourier transform or Bessel transform or Laplace transform, if you want it, can be expressed as a matrix product. So these are the family of problems that will very nicely fit your modern architecture. So this is the quantity you have to think about when you want to parallelize on the architecture that we will see during this school. If the only tool you have is a hammer, you tend to see every problem as a nail. If the only tool you have is a GPU, you tend to see every problem as a matrix product. So, as you have already seen in a different light, the computer is a Turing machine on the standard von Neumann architecture or Princeton architecture leads to the von Neumann bottleneck. You take some data from the memory unit to the arithmetic and logic unit, and you return it. And this is controlled by the speed of your memory, which we have seen is quite bad. So the Harvard architecture, not so far from Princeton, had the trick of getting instruction memory and data memory. And this is what we find with the level 1 cache, which is on the one hand data cache, on the other hand an instruction cache. Okay, so you also have to keep in mind this kind of orders of magnitude of how much time is taken by each kind of operation. So you want to pack as much things on, not wait for a very long time or detach the weight to some other thread. You have to know on which machine you operate, for instance, with this HW-lock LS that will display what you have also already seen. Different generation of CPU with the L1, L2 gauge not changing much, 32K for the L1 instruction, here 48 for the L2, L1 data, but okay, L3 is stuck at something like 24 megabytes only. One more reason to parallelize is that when you will quit this school, you will be back to your labs and your colleague will go to your office asking for some speed up. So some generality about the kind of programming that this landscape puts on us. We are all used to imperative programming, programming sequence of instruction and giving a set of subtasks to the processor. It's an order shopping list, it's an ordered recipe. And so the first meeting with programming that we have is something based on sequentiality. This is essential to programming. But to exploit many cores, we have to think differently and to understand that with only one processor, the task will get executed one after the other. But even with only one processor, sometimes this order is compulsory because permuting task would change the result, but sometimes this order is contingent and permuting task would not change the result. So we want to understand clearly in which is which. If we can identify all these permutable tasks, we could run out of sequence, and we could run those concurrently if we happen to have multiple processors. So the first aspect is to identify the task in your process and see which can be reordered. And you can think about this concurrency, this exhibiting concurrency in the program as an industrialization process. So on the logical level, we want to identify tasks, and among them, the order-independent tasks. But on the physical level, we want to assign those tasks to execution threads. So in the old time, you were not born, and multitasking would occur on only one processor because it would distribute the task to the only thread that was running. Or it would share the time between different threads on one processor. So there was a minimum loss with context switching. It induced a time sharing of processing resources, not only the processor, but also the screen, the disk, and so on. And so if you have a multiprocessor, each processor can be assigned one or many threads. And what we call parallel programming or multiprocessing is concurrent programming on a multiprocessor. So you have always this exchange between the logical level and the physical level. So most of the time, we have lots of loops, and we have, in fact, two kinds of loops. We have the iteration that depends on the previous one. This is what we can really call an iterative process. If you are polishing some wall before painting, you will start with the coarse grain and finish with the fine grain. You cannot change the order or the result will be really bad. On the other hand, we have iterations that are independent of the previous one, and so it's more a duplication or an enuplication than really an iteration. This is what people call, for no good reason, embarrassingly parallel, and the lowest possible concurrency. The processes are as decoupled as processor, but in fact, there is nothing embarrassing. It is delightfully parallel. We are looking for this kind of processes. It's very common in particle physics. Each event is independent and can be processed on a separate processor in a separate process. It led to something which is easy in some sense. We buy more computer and we distribute the independent processes. We distribute the data. All the parallelism is in changing the data with the code being the same and independent. It then leads us to something that is related to functional programming. When we apply the same function on a collection of objects, the collection of results is independent of the order of application of the function. So we expect this in parallel settings, and to ensure this, that this is right, we need so-called pure functions, which are computer functions that are as close as possible to mathematical functions. First point, the function returns value are identical for identical arguments. It looks nice, it should be okay. It should not depend on some local static variable, non-local variable, mutable reference argument, input stream. Its evaluation relies on a deterministic algorithm. Given a particular input, it will always produce the same output with the underlying machine always passing through the same sequence of states. And we call this function as referentially transparent. On the other hand, we also need that the function application has no side effect. It should provide result without mutating local static variable, non-local variable. You can think of global variable, of course, mutable reference argument on input string. So pure functions are deterministic and without side effect. So with pure function, I am telling you something that is explicit in modern Fortran, but it exists. You have to think in these terms in any other language. Okay, so we started with imperative programming, but we are inserting slowly more functional paradigm, which is needed for expressing parallelism. So input arguments must be immutable, so you do it in C++ with const arguments, in Fortran with intent-in. Evaluation must not rely on mutable global variable, so in Fortran, you should not take a common variable, but only module parameters or protected variables. In C++, you can use const, const expr, static const expr globals to make them non-mutable. A pure function, in turn, can only call pure functions, and you should not raise any exceptions. So all these requirements on top of one another have very direct consequences. The most useful way to debug a program is to insert some print somewhere. We have all done this. But when your function is pure, input-output is mutating something somewhere else. So you have not the right to use input-output function, and you need to know your debugger. And you need to have a set of tests that will test the function without you needing to debug it. The expression can be replaced with its corresponding value without changing the program's behavior. This is the meaning of referential transparency. And this allows memorization. If your computation is very intense, it has consumed a lot of data, you may not want to redo it. So it's good to store it somewhere. And the next time you will call the same function, in some languages, but not the one we'll be using here, the function will look at the cache instead. So there is some trade-off between memory and computation, and as we have seen, it depends. If you have a very short function, it is better for you to recompute it. If it's less than 80 operations, okay, don't bother storing it into memory, recompute it. But if you turn over this function time and times again, if you can organize your cache optimally, then memorization is a good thing. So some people speak of this as a lookup table. It's a specific type of lookup table. You compute it once, or you read it from a file once, and your program uses it many times. So usually they are initialized at start, as on the other hand, memorization fills it on the fly. So your generation is familiar with object-oriented style of programming, and you need to think in functional aspect as well. But whereas object-oriented is most of the time some object, some data surrounded by a swarm of methods that operate it, functional programming, once the object is created, doesn't change it. So it's always good to think in terms of object, but in fact, you have mostly one constructor in a functional object and accessor, but read-only accessor. So as you get more familiar with, as you get your program to more concurrency, you will see that it changes your style. Okay, so what can happen when the function is not pure? Or what can prevent the function from being pure? We have seen input-output, displaying something occurs in a given order. So a pure function cannot be dependent on this order. Storing data to disk goes the same. You can see the data on the disk as a global variable. So your pure function cannot write. If there is anything hardware related, depending on the interaction with environment, which is a global variable, the environment, your function will not be pure. If you read the temperature, you are not guaranteed to get the same value afterwards, particularly every summer. And time dependency in any kind of program is a no-go for purity. Your access to the clock will return a different value. Exceptions make your function not returning a value of the expected type. So in mathematics, no function has exception. And what you do often in math is extending your function. You all know of the factorial. It is defined first on integers, on +1 at least. Then you extend it to the gamma function on real, and you extend your gamma function to the complex plane. So you try to expand the definition domain as much as possible, Of course, the typical impure function is the random number generator, most of them, because it has been, well, almost 15 years that we have cryptographic, like random 1, 2, 3 generator that are index-based random number generator, counter-based random number generator. It's a bijection, it's a one-on-one map from natural number to natural number. It is fixed, it will always assign to order 1 some improbable value, but always the same. When you want to have simulation with concurrent random number generation, you need this kind of random number generator. Of course, if we want to be dark, in the long run, no computer function can ever be called pure. Running a computer requires energy. Running a computer increases the entropy of the universe, which is a global variable. Ergo, no functions are pure. No computer functions are pure. Well, a short warning that will resonate in the end of the week. Most of the computation we'll do use floating point evaluation. And they are usually dependent on the order of evaluation. When you have floating point additions or multiplications, they are not associative. They are commutative, but not associative, contrary to what we are used since primary school with a real number, with any kind of number that we know. Nobody has used octonions. Okay, so for you, everything is associative. So the fact that your loops will compute sums or products out of order might change ever so slightly the result. So the compiler will tell you, okay, your function is pure, but is even lying to you. if you have addition or multiplication. But if you don't have this kind of operation, then you don't do HPC. So there are subtle side effects introduced by the language because C is a low-level language, close to the memory model of the computer, and it strictly conforms to your order of computation, mostly. This is the general philosophy. Whereas Fortran, the first name was a formula translator, tries to somehow optimize your computation. You say, I want this formula computed, and the compiler organizes the order of evaluation. So sometimes mathematical equivalents are not numerical equivalent. And you have to be conscious that there is this distinction between the purity check by the compiler, which are rather formal, and the purity floating point check that are, in my knowledge, not done. Okay, so when you have a pure function, you want a reentrant subroutine where multiple invocations can safely run concurrently on multiple processors. When you are not sure your function is pure, it can at least exhibit some reentrancy. On a single processor system, when a reentrant procedure can be interrupted in the middle of its execution and then safely be called again, because on monoprocessor, the system will attribute some CPU time to your thread, to your lone thread. So the reentrant code may not hold any static or global non-constant data without synchronization. And synchronization means waiting, and waiting is losing time. Reentrant code may not modify itself without synchronization. Yes, we are not so much used in your new generation to code modifying itself, but it was once a very profitable way of living for computer guys. Reentrant code may not call non-reentrant computer programs or routine. On the other hand, you have so-called thread safety, which only manipulate shared data structure in a manner that ensures that all threads behave properly and fulfill their design specification without unintended interaction, so-called data race, when two threads operate on some common memory. And these two characteristics are not equivalent. You can have reentrant code that is not thread safe and thread safe that is not reentrant. You can look at the link in the description to see examples that are really a bit convoluted, but present anyway. So some tasks can need to take the lead. In this occasion, we speak of a critical section, a part of the code where concurrent access to shared resources would lead to erroneous behavior. We need to protect these accesses. Usually it is done with lock and mutex. So as for synchronization, we have many threads that are waiting for the lock to open. And so they are losing time. During a critical section, we lose all benefit of the multiprocessor, and it can lead to the delightful deadlock where each thread is locking the other on your program that was working in monothread is now stopping. Okay, so the aspect, the remaining aspect that has been very much sold by Sébastien before is vectorization. So as we have seen, parallelism as scales. The easiest way of parallelizing things was when you could buy multiple computers that each was monoprocessor. And so with some network, you would transfer the data between the process and you would organize processes as you organize coworkers. Because you don't know what happens in the head of your coworker, except when you ask him or when he tells you. So you can see processes as separated, well-separated environment. So it applied nicely to embarrassingly parallel problem, the one I called in particle physics. It led to a bunch of technology for inter-process communication, like in Unix, pipe, shared memory, semaphores, and with separate computers on the network, it led to distributed memory systems such as PVM, the old one, and MPI, the very common, worldwide known message passing interface. Then, when multiprocessor became more common, we had threads, so-called lightweight processes. They are very much like Canada Dry. It looks like a process, but it shares the same memory. It's nicer because you don't have to organize formally the exchange of cards between the processes, but you can be working on the memory of the other process, which is a big problem. So in the end of the 90s, we had the C++, C and C++ POSIX threads. We had the ADA task from 83, as well as the protected object in ADA from 95. And the OpenMP that we will see in the implementation of the code, it started in 97 with a very basic and efficient model that we'll describe. But what I want to discuss now is vectorization, because even threads that are lighter than processes can have too much overhead when the concurrent tasks are elementary. If your task is not big enough, it's no use to put it in a thread. But sometimes there is parallelism, there is concurrency that you can express at the data level. It's something called instruction level parallelism. We had vector processor à la craie in the early 90s. We had some lucky ones had vector processor à la craie, but it was not well known. But at the end of the 90s, it started appearing on everybody's computer with MMX and SSE, and it never stopped increasing since. What are these kind of instruction level parallelism? We already know the bit level parallelism. If you have ever applied a logical mask on some data, you have a bit operation one-on-one. So when you end two integers, you end each related bit at the same time. So we want the same kind of operation, but instead of having a bit-by-bit operation, we want FP16, FP32, floating point 16, floating point 32, floating point 64 operation in one instruction. So in the same way, for our vector instruction to perform fluently, we need to align our vector of data. Octets, bytes, sorry, they are aligned. But when you go to data structure with 512 bits, there is no guarantee that the 8 first are aligned with the 8 first of the other, the memory boundary. So we have better order data of same nature as an aligned and contiguous array. Both are important. And for data contiguity, we need to shift our usual object-oriented point of view. And we want to prefer a structure of array to a collection of objects, which is an array of structure. What does it mean? If you have a structure of array, if you have a structure of array, you will have, let's say, the 8 first member of the object aligned. They have the same nature, they are the same type of data, and the second component of the object will not be intertwined in memory. And so you can use vector operation that needs homogeneous data. Changing this is non-obvious. When you have a program of some size, you think to it twice before modifying such thing. And as I have said, for expressing concurrency, vectorization is certainly an industrialization process. You can see your computation as a production line. Here, Charlie Chaplin is operating 2 data at a time, whereas his colleagues are operating scalar and not parallel. Okay, it's the minimum level of vectorization. So in the end, you want to have a kind of pincer movement around performance. From the top of your problem, you want to parallelize to expect concurrency at the level of the task. But from the bottom of your problem, you want to express vectorization at the level of the data, of the individual data. And as we are in 3 dimensions, we need to extend the pincer movement by keeping the catch hot on top of this. So, after all this theory, how to vectorize, you have many solutions. There is a tedious and efficient one. You uncraft your vector code yourself with dedicated low-level instruction. You use a plus on vector of data, you use a multiply on vector of data. It's tedious, it's very dependent on your architecture. It will not pass smoothly to the next computer. The second solution is to use vector library. Some people did the job for you. You don't have to know the details. This is the one we advise to most people. The third part is where it goes really hard. We let the compiler do it, provided we can express the data parallelism, which is some high-level aspect. So when you can, à la MATLAB or Fortran 90, harness the power of array, you are giving the compiler some way to know that there is some data parallelism to be used. Some aspect that goes opposite to the first one is to hint at the compiler for data contiguity and alignment. On the first level is a high-level aspect, on the second point is a low-level aspect. And so depending on your language, in C, you will relatively easily tell your program that this data should be allocated aligned with memory. And this data that I pass a pointer to is in fact, I swear, allocated in memory. And if you don't comply with what you have sworn, you will have a segmentation fault and your program stops. So high-level languages handle easily the first part. Low-level languages express easily the second part. we have to combine them. And of course, you will not put any kind of confidence to a computer, so you want to check the result. But how do we check that some function has been properly vectorized? So you have to know the specific flags of your compiler to report what it does as a vectorization. You have to know the specific flags to tell him to vectorize explicitly. You could check the resulting assembly. Anybody has ever read much assembly code? Well, so what was your experience? Okay. Some people like it, but yes, at least nobody has to write assembly, but some knowledge of reading assembly can be helpful. But let's acknowledge it, it's a bit tedious for most of us. As you will be shown tomorrow, there is also Macao that does an excellent job, provided you have sufficient antidepressors. And indirectly, you can use perf that will not use too much here. Last point to finish. Sometimes there is a kind of symbolic vectorization. When you use complex number, you use pair of number. When you use quaternion, you use quartet of numbers in one go. So on the symbolic level, you do many things in one high-level operation. But this symbolic vectorization gets in the way of practical vectorization, because as you can see with this explicit complex number multiplication, if your number are just one pair of complex, then the real component and the imaginary component are intertwined in memory. So the operation that you would like to do will not correspond to any vector operation on your instruction set. What you want is to have a complex of vector in some way, where A1, A2, A3, A4 are contiguous in memory, and B1 to B4 the same. And with this kind of data structure, then you can vectorize complex number. So you see that most of your program have to be rewritten in the hard way to exploit to the best this kind of vectorization. So that will be all for this part. Yes, so we take a 30-minute break, and the next session will be what is compilation with Pierre Aubert.
Okay. We're live, everything is working. Okay. Okay, so hope you have a nice pause. So we'll start to talk about compilation because it's a core problem of what we do once we want to optimize stuff. So what is compilation? How to do interesting stuff with it? So basically, compilation, the goal is to convert text to binary. And then whatever binary you want, it's okay. So you get some sources, and then you call the compiler, and you get some object, a .o, if you do some well stuff in the build directory. And then you have the linker, and the linker will get all the .o, the object, and we put everything together to get a library or a program. And then the program will run on hardware. So it could be CPU, GPU, whatever you want, depending on the backend of what you want. Here we can optimize several things. So the compiler will try to optimize some stuff at its level, because of course the compiler cannot see the whole program here, only one file. And the only program which is capable to see everyone is the linker. So the linker can do other kind of optimization. And maybe you have seen this option, the LTO option, the link time optimization option. So you get that in NVIDIA compiler, in Clang compiler, LLVM compiler also. So the idea is to have the whole control of what's going on in the program and be able to remove generally dead code. But we'll see that a bit later. So how does it work? So first you start with your favorite language, and then you want to get some binary at some point. So we have what we call the front end. So the idea is to just parse the text and get a representation of that with the grammar, the syntax that you want for the favorite language you want to use. So then we have the middle end, so an intermediate representation. So in fact, there are several intermediate representations, but let's simplify it a bit. And then you can start to process some passes on your intermediate representation to do some optimization, for example. So first, we'll try to remove the comment. That's quite common in the compilation. And then let's solve macros. But maybe some macros will create some comments. So maybe we want to remove comment again after that. And after that, maybe we want to remove some dead code because, of course, some macros might create some dead code as well. And at some point, maybe we want to have a look into the constant forwarding. So the idea is you write a program, you create a variable with a constant in it. And you don't want, of course, to copy this constant yourself. The compiler can forward it for you. So that's a good point, but maybe you forward the constant, and at some point you will have useless call because you can solve some calls, some condition that they are always right or always true, and then you can remove the other part of the branching. And so you can remove again that code. You can have a look inside the loop at some point once you use high-level optimization flags. And maybe you will figure out that inside your loop you have some dead codes as well. And again, you can remove some code. And of course, that's a recipe. And all the compilers have their recipe, and you can guess what's going on. And you do that many times with as many passes as you want. And for modern compiler, it's 150, 200 steps, 300, depending on the compiler, depending on the level of optimization you want. So that's why sometimes when you compile, it takes a while, because of course, you have a lot of things to do. And the problem is you cannot check if the pass could do something. So you prefer to run the pass on your intermediate representation, and maybe the pass does nothing, but way faster than to check if it's important or not. And then we pass to the backend, and the backend we figure out, okay, I have this representation, I want to match this hardware, so I have to say, okay, this instruction, this condition is this binary, etc., etc. So what do we do with the intermediate representation? So a program is a graph. And once you have a graph, you can update the program as you want. So for example, you can say, you can add probes. So you can say, okay, let's add some, let's check some compute instabilities. For example, if you use some verificalo, some program like this, you can do this kind of gprof stuff. With gprof, you can use the compiler. You can put some probe inside all the function to see where you are calling them, the time they are needed to be run. You can do some unit testing if you are using gcov already. That's the kind of stuff that you do in the compiler. You put some counter on each line of your code to see if you pass through them or not. The same for the branching. Then you can optimize. So you can forward the constant, you can inline, you can auto-vectorize, you can auto-parallelize. A lot of things to do here. But the result has to remain identical, and the compiler cannot change the graph. The graph as input and in output should be similar. So sometimes we'll say, okay, the compiler is stupid, it cannot optimize my function. No, maybe the compiler is not allowed to optimize your function because the graph will change, and the compiler is not allowed to change the graph. So the compiler is not stupid, it just does not have the right to do that. As a developer, you can say, oh, I can break my graph, I can change the order of the computing, no problem. But the compiler cannot do that. So in terms of option, if you see the documentation, you will have the O0, the default for GCC or G++. And you can also debug with OJ to have some flag here. O1, so really simple. We forward the constant, we remove some dead code, but not too much. Then O2, partial function inlining, and assume strict aliasing also. O3, more function inlining, but loop unrolling. We discussed a bit about that a bit before. So here you start to unroll a bit, to vectorize partially the function. And in OFAST, we try to do as best as you can. So you say, okay, we use fastmath, we enable FMAs, we potentially degrade a bit the result if you have values which are not well bounded in your graph, in your matrices, in your vectors, things like that. So you have to check. Every time you want to use OFAST, you have to check, or otherwise you will have a problem. But if you do your job well, normally, if you use OFAST in the right condition, you should get a nice speed up. So let's start with an example to see what's going on. So if I take this function to compute the square of a number, and this main, I can start to forward the constant. So I have a variable y, and I put directly the value in the call of the function. That's constant forwarding. You don't have to do it yourself, of course. That's the job of the compiler. Then I can say, okay, let's inline the function. So you replace the body of the function directly when it's called. Of course, it's okay for a really small function. If the function is too big, you will have a problem of the binary size at the end, and you will have jump, will cost a lot after. And finally, you get only constant, so you can say, okay, let's compute the result. And at the end here, you have no call, you don't have computation, you don't have variable, you just have a print, and that's it. So sometimes you can get tricked by the compiler itself, by this kind of stuff. So you can also unroll, we talk about that a bit later also, a bit before. So if I take an Adama product, of course, so basic Adama product with one computation in the iteration, I can say, okay, let's unroll it a bit by hand here, and let's compute 2 elements for one iteration. So I increase the computing of an iteration, and I can do the same with 4 iterations. So I check less the condition to stop the loop. So the idea of unrolling is to check less time if you are at the end of the loop or not. So if I do not unroll, every time I perform an iteration, I will check if I am at the end of the loop. Of course, it's a bit too much, especially if the loop is long. So you want to say, okay, let's enroll twice, and then, as Sebastian mentioned, the branching predicator stays cool, because of course, if you ask it less time, maybe it will get wrong less time also, so it's better. If you do some optimization and you have a stencil, that's our case for Grayscott, a 3x3 stencil. If there is no unrolling, I compute the stencil and I have one result. So 9 load, 1 store. Not really nice for the memory. Remember of Sebastian with the memory. Not so good. If I unroll twice, I have the 9 load of my first iteration, and then I will load the 3 more values for the next one. And of course, it's better because I have 12 loads, but 2 stores. Kind to improve a bit stuff. So 2 loads per, 6 loads per store, better. Not that good, but better. If I unroll 4 times, so I have this one, and this one, and this one, and here, 18 loads, but 4 stores. So 4.5 loads per store. Again, much better. And of course, here I consume practically no memory at all. Remember the cache size, 32K, so you can put a lot of values in it, so no problem. Question already on Discord? Question on Discord. Sorry, Sebastian, we will be late. Question. Technical question, I believe. This one. The size of the result. Once you unroll, except if you have a lot of, if the compiler can simplify a lot the computing after that, because of course you unroll, but sometimes you can do some optimization after that, and you can reuse some result. Generally, it increases the size of the program. It's quite normal. So yeah. Always do that carefully. And something important also, if you enroll a lot, or maybe you want to enroll and the compiler don't want to enroll, and you say, oh, the compiler is stupid, I want to enroll, you enroll by hand, and you figure out that you don't have enough registers. So it was a bad idea to enroll, in fact, in that case. So remind every time that once you enroll, you use twice, 4 times the number of registers you want to use, and you don't have an infinite number of registers, and you have less vector registers also. So it's important to not to use too much, only for what matters most. So here, it's really important. If you use too much register, you will have a problem. So compiler can also optimize sub-expression. So if I have this kind of expression, so b plus c times b plus c, because can happen sometimes, I have a graph. This can be done after some other, of course, simplification. If I forward some constant and the constant becomes 0, I drop the constant for my computing, and I can have something like this. So I have load B and load C, and then I do the add, and I load B and load C again, and I multiply, and I get my result. I store the result. Okay, that's assembly with nice color. So if I write it another way, load B, load C, I perform a add, load B, load C, and perform a add, and I multiply and I sort. Of course, too many loads. I want to decrease the number of loads. So what we can do is to duplicate a result. The compiler can say, okay, I have an add, normally, but then I can duplicate directly on the stack the result, and then I perform the multiplication directly. So I don't have to load again and to compute again in addition. And then I sort. So this is a kind of really small optimization that the compiler does everywhere and saves you a lot of time, of course, because you will use your table, you will load the table, and maybe just after you will reload your table, but the compiler will understand that, okay, it's not necessary, maybe I just have to duplicate a result and it's much faster. So in terms of implementation, let's start with an Adama product. Let's pretend that I want this, I have this Adama product, and I want to check the time, the execution time of this Adama product. So I will write something like this. And I will say, okay, let's allocate the table first. Then I initialize some values, random values in the table. I start a chrono, timer. Then I do some performance evaluation, so several times. I stop the chrono, and then compute the time, number of elements, computing per element, stuff like this. And I print the results, I deallocate, and it's okay. Okay, what are the results? We do that with hard-coded boundaries because I don't have time, but of course it's better to have something nice with the parameters. I get that. So on top, it's okay. Can understand expected performance on a laptop, no problem. But come on, not really logical. There is a problem here. 0.001 nanosecond to compute 1,000 floats. It's really fast. It's a bit too fast. Yeah, so it's a bit too fast. Let's be honest, it's my laptop, it's this laptop. It's 4 gigahertz, not 1 petaflop. I don't have 1 petaflop in my laptop, come on. So there is a trick. There is something which is really strange. I ask Clang, and Clang is, okay, no problem. Come on, Clang. No, that's silly. It's not reasonable. Okay, I ask ICPX. We have a problem. We have the same strange behavior here. So what's going on? Why do I have such strange result? The compiler will get the result. We'll see the results variables, the table here, and say, hey, we don't use the results. We compute it, but we don't use it. So can drop it. And then if I drop the result, of course, the loop is useless. So let's remove the loop. But if I remove the loop and I remove the result, I don't use these variables. I set the variable, but I don't use them. So let's remove the variables. And of course, you see me come, this loop is useless. So let's remove this loop. And at the end, what do we have? A start of the timer next to the stop of the timer. And of course, makes no sense. It happened to everyone, so it's normal. So here, the problem is, of course, the compiler sees everything and say, it's useless. Let's drop everything. So if the kernel is in the same file as the function to evaluate it, of course, you will have a problem. If you change the kernel, if you put the kernel in another file, as I said before, the compiler will not have the knowledge of what's going on in the other file. So maybe there is a variable, global variable somewhere. The compiler cannot make assumption on this function. So we'll call the function because maybe something will be modified at some point. Or you can use a std vector. It's possible also. The compiler will not bother you with std vector. Or you can also print the result, even of the first element. You don't have to print all the elements of the vector, but if you print the first one, the compiler will say, okay, you use the result, I will compute the result, no problem. So that's a little trick. If you have strange results, always think about the compiler, because maybe it's not really its fault, but could happen. So if I fix my problem, I will get this kind of result. So kind of normal stuff. So here you see that, of course, these performances are a bit less good as the performances of Clang, of course. Here, I'm not here to tell you that Clang is better than G++11. I'm just here to tell you that they disagree of what is O1, O2, O3, and O-fast. Just that. So here you can say, okay, O0 is the same, no problem. O1 is the same, no problem. O2, okay, here O2 we do practically nothing, and here we start to partially vectorize, because Clang wants to partially vectorize once you use O2. Because it's a different compiler and they do what they want. So it's not a norm. And the same for O3 and OFAST. You start partially vectorizing with O2, so of course all the rest start to partially vectorize. Of course, it's not what you want. If you vectorize, of course, again, if you vectorize well on G++11 and you vectorize well on Clang, of course you will get the same performances. Normal, because you get the performances of the machine, so it's normal. But if you don't get the performance of the machine, they will disagree of what is the default also, because O0 is not the default of Clang, last time I checked. So you might consider sometimes and say, okay, Clang is better than G++. G++ has a default as O0 and Clang has a default as O2. So of course, disagree of what is the default, and you will say, okay, by default, this one is better, but we don't care about the default. So in terms of some mistake we can do also with Clang, which is nice also to have. So I have this kind of Adama product. I'm proud of me. It's okay. I put everything to vectorize nicely. So we'll see the detail tomorrow. So I use the right option. I use the right assumptions for the alignment, stuff like this. Everything is nice. And I have a problem because this is an unsigned int in the loop. So 2 power 32. And this is a size t. So a long unsigned int. So 2 power 64. And the problem is the compiler is smart, and the compiler can prove that this condition could be always true. Because you can have an infinite number of iterations, because in this kind of problem, an overflow of an unsigned is a defined behavior. So you cannot do whatever you want once you have an overflow of an unsigned. You need to loop. And the compiler knows that. So the question is, and I like this question, does infinity a multiple of 8 if you want to vectorize in AVX? Of course, the answer is no, so there is no vectorization. And this is why if you look at a lot of examples of code from NVIDIA, for example, for NVC++ or NVCC, you will get some integer instead of unsigned integer. Because once you have an overflow of a signed, it's an undefined behavior. So the compiler can do everything you want. So you can have extra optimization that you cannot have if it's an unsigned. So that's a trick question. Discord question, okay? Okay. The professor, compiler explain again, but the compiler skips the loop of Adama. Yeah, the compiler skips the loop of the Adama product because we don't choose the result. So the compiler knows that we don't choose the result, and since we don't use the results, computing makes no sense, the allocation makes no sense, and so we drop everything, including the call of the function, because we don't use the result. We don't print the result, or we don't store it in whatever place. Okay, that's okay for this part. So let's take an example for the reduction. So if I write my for loop here, so don't blame me, Vincent. I'm in the cache. I do a sum with 100, 1,000 elements. So I don't have 1 million elements with a sum like this with a float, which is a nonsense. So it's okay. But you always have to check. Of course, a sum like this with 1 million elements is just crap at the end. But we'll see that a bit later with Vincent. So it's an explicit order. So we will assume here we don't need the explicit order because it's really small, and I have nicely classified values, and I don't have much difference between the smaller and the higher value in my vector because I did the thing right before. So you can use std reduce in C++17 or C++20. Do the reduce for you. With parentsec, I showed that a bit before, if you want the compiler to auto-vectorize or auto-parallelize this kind of stuff. And if I use a basic option, of course, I get quite the same result, even if, again, G++11 and Clang 14 disagree on what is 1 or 2 or 3 or fast. But if I vectorize, at some point, they are stuck at the same place here. But of course, If I want to use a reduction in intrinsics, so I want to force the compiler to optimize what I want to do, can have a much better, much faster code here. Because again, in this case, the iteration of the loop returns an integer or a scalar, at least, a float, a scalar. So you can, what we do is inside the loop, we load a vector register, we add it to the next vector register, and then we sum the vector register to return, for the iteration to return a scalar for the next iteration. So it's a weird vectorization. Once, of course, you want to do that before and after the loop, not inside the iteration. That's a big problem, but the compiler cannot change the graph representation of your program. So compiler cannot do this optimization that I can do. But if you use std reduce, you can, because the std reduce will do this kind of result. So practically the same performances are really close, even better here. So really nice. So use std reduce if you have some doubt, you will get much better performances. And of course, since I don't want to be beaten by a compiler, I can say, okay, but I can do that. So I can unroll and interleave a bit more with intrinsic function, this kind of stuff. And the compiler cannot do that. So how can we do this kind of magic? So as Sébastien explained also a bit before, once you compute something in your pipeline, your CPU pipeline, you will have to wait an elapsed time until you can get the result and use the result back. So you can vectorize. You can vectorize 4 times, 8 times, 16 times, what number of times you want, but you still have to wait a certain time for the hardware to give you the access to the result. That's the time for the Vectron to move, so you have to wait. The problem, of course, if I have only one accumulator, I start my computing and I wait. I practically wait all along, and that's a pity. So the trick I can use is to use 2 accumulators. So I use the first one, and once I wait for my result, I pick the second one. Of course, I cannot compute two reductions at the same time because there is only one compute unit for this one, for this precision or this float, for example. But I can compute during the other is waiting. And of course, with this scheme, you can use 4 accumulators for this really simple computing, and it's okay. Of course, if the computing costs much, the weight is less, and maybe you cannot fit enough computation in the weight. So typically for reduction, you can enroll for 8 times. For barycenter computation, only 2, it's okay normally. For modern CPU, at least it's okay. So if I do that, so I start my classic vectorized version. I get my intrinsic version. I can vectorize and interleave twice. I can vectorize and interleave 4 times. So here you see that G++ is unrolling my interleaving automatically because it understands that it's possible, and Clang will not do it. So here, G++ is smarter than Clang. And then, of course, if I unroll 8 times and interleave 8 times, I get the same result, of course, because I have the best performances possible on my laptop. So every time you do a performance test, always remind you that are you measuring what you are thinking you are measuring? Because it's not trivial. So a performance test will evaluate always with a given method, so more or less precise, an implementation, more or less quality, maybe it's not a good implementation, of an algorithm, so maybe it's not really the algorithm you want to use, maybe it's another algorithm you prefer. Compile, but maybe you forget to put some flags, or maybe you put too much flags and you broke the result. It's possible also. On a computer, but with the computer you can have a more or less efficient computer, and maybe the resources are shared or not. Maybe you are not alone on the machine and you will have some problem if a process will kill the bandwidth of the A3 cache, for example, and you will broke your result. With a dataset, if you do some image processing or some data processing in general, with maybe the dataset is more or less representative of what you want to do. And during a certain elapsed time, because of course you don't want the test to be too long, but maybe elapsed time is not as good as you want. Maybe it's too small or too big. And we'll have, if it's small, it's nice, but maybe you are just in a warm-up and the CPU is not at its full potential. If it's too long, maybe you have too much interaction and noise for the other program running at the same time. So that's a trade-off, and that's quite difficult to get the right point here. And of course, you are on an operating system, and Sebastian will show that, of course, an operating system can be really horrible to use and do some stuff under the hood and you don't want, and you have to fight against it. And yeah, so you can have a lot of problem with this kind of performance test, but it's important to remind you that, okay, you have a lot of things which are not really under your control, so you have to check everything to be sure that your performance test is really nicely done. So I will finish, practically on time. Okay, we are late, but not too much. I will finish with some stuff which are maybe not too much well known in compiler. It's certification. Because sometimes, of course, writing a compiler, it's really hard. I'm pretty sure that I was able to show you that. But sometimes you want the compiler to be certified. For example, if you want the compiler to build a binary to run and to fly a plane, because of course a plane, if there are people in it, you want the plane to fly well. And the compiler should be certified at the level of the plane, of course. So that's not really trivial to do. And C-Smith was developed with our colleague of Enria a bit more than 10 years ago, 15 years ago. And it's a C generator. So you generate perfectly well-designed C code. So you respect the C syntax, the C semantic, the C grammar, and you try to generate stuff which are in the corner cases of what the compiler expects. Because of course, there is a grammar. The compiler is implemented by people who try to be as lazy as possible, because again, sometimes, and all the corner cases you don't really check because nobody is writing this weird stuff in this way, so there is no problem. And sometimes, yes. And they did that, and they found hundreds of bugs in G++ of this time and Clang of this time, so 2009 or 2011. So typically G++4, stuff like this. So if you know people, there are, unfortunately, some people are using G++4 already, even if G++4 is died in 2011. So be careful, you have a lot of bugs in these compilers. And of course, that's nice to break a compiler. And when I say the compiler is broken, just to be clear about that, if you give a program to the compiler, and the compiler have a segmentation fault, okay, the compiler is always right, but in that case, it's not a bug, just something which is not expected. Okay. If the compiler gives you an internal error, okay, it's not a bug. If the compiler gives you a panic, it's not a bug. This kind of bugs, it's the compiler compiles, gives you binary, but the binary is wrong. That's a bug. And once you want to fly a plane, you don't want this kind of bug, of course. And since the team, it's the work of the team of Gerard Berry, and since it's not enough, of course, they developed a compiler, CompCert, which is a certified compiler, at least the only certified compiler I know. So the idea is to mathematically prove the compiler, and you run also C-Smith on the compiler, and everything works perfectly, and there is no problem. So it's possible to prove mathematically a compiler. It's really hard, of course, but you can do that. So that's for a little bonus of this presentation. In conclusion, don't choose a compiler, pick all the compiler you can and compare the result and be sure that, of course, they agree on what is vectorizable, what is a result, stuff like this. If they all disagree, maybe you have a problem in your program, something is not really well defined, or you have some ambiguities or stuff like this. So it's important to have a look always. And of course, but we will see that tomorrow, always check with Macao or Valgrind, but much Macao, if the compiler does his job well, because of course the compiler will compile, you tell the compiler to vectorize, and the compiler will say, okay, it should be vectorized, and you say, no, I will check if it's vectorized. It's better, not only for the performance, but for the binary itself, you can check. And that being said, thank you for your attention. And well. Okay, we are 10 minutes late, but come on, it's well less than before. So if there is another question, or maybe in the audience, if you have some question, we will play with everything tomorrow. So normally it should be okay. Okay. And now we will do some unit testing with Sébastien.
So we'll speak about unit tests, and they didn't unit tested this virtual box with changing the screen. Ouais. Sorry, I have to launch again my. Okay, we go. So let's go for another topic. So we have spoken now about performance, hardware, complex stuff. Now we'll make a kind of a bit refreshing talk. We'll go a bit higher in the software layers and on our computer scientist life, or physicist, depending on what you are. Unit testing, a philosophy and an help on our applications. So here I will speak about kind of giving kind of feedback, because I'm making unit tests myself for the last 14 years. And this is something I like a lot, and I want to share why it's a good thing to do, especially if you want to have performance at the end. So I will first start with a kind of carrot, why I started to make unit tests, a little bit of philosophy and motivation. This will be a bit refreshing. We will go in a real life problem, something else than computer science, to see how we make things and why in computer science sometimes we make things in the wrong way. We will think about the testing methods, and I will give some feedback on my own experience and feelings about using this methodology. I will give you during this presentation a bit how I look at this problem, the glasses through which I'm looking at it. And if I have time at the end, I will give you some timings to show that you win in terms of validity of your code, but also sometimes in time. Because of course it costs a bit at the beginning, but I will show you that you can win in the end if you apply it on a long-term development. So why I started? So once upon a time, a long time ago, time has passed, I was a master student in 2009, and I was developing a Linux kernel module at CEA about memory management. This is my domain, you will understand, memory management. So I passed 5 months to develop my kernel module to make some optimization on the memory management side of the kernel about this domain. And after 5 months of development, I was able to run my full KDE session on top of my module. So I was very happy. It's working. And of course, we were at CEA. So at CEA, we are making numerical simulation, large one. The large one we were working on at this center was 1.5 million lines of C++ code, 16 threads at the time, because the machines were smaller at this epoch. And we wanted to test, of course, at the end of my internship, if this application is optimized by the changing I was doing for this work. So I started one day, they came to my office, we compiled the application, we started to run, we started the application. It was running for half an hour. Yes, started running, everything is fine. Started, we see the message printing, saving data, etc. So I was, it's running very nicely. And then crash, kernel panic. So kernel panic, when you develop in the operating system, you know, if the operating system is buggy, it makes a kernel panic, so you have nothing. You have no debugger, no way to debug. Good luck to find your problem. So I was not very happy. I passed 2 months to make a kind of logging every calls which were made to my kernel modules, which were something like 75 million calls during all the run of the application during half an hour, and try to guess from this log to replay it by replaying it which sequence was causing my problem. So 2 months to debug that. So when I was a student at school, after that I started my PhD over malloc to implement a parallel malloc and working on the operating system also, still continuing this work. So I say myself, maybe I will try to use a different approach to not get again the problem. And during my school, some people were speaking about, I had a teacher like me who was saying, yeah, unit test, this is a good thing, blah, 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 blah. And I say myself, yeah, okay, maybe I can take my path on it and try the methodology. And I applied it. I was lucky because during my PhD, I was able to apply it 100% on everything I made. And the conclusion for me was it was very great and very nice. So I will try to share a bit what is the path over that. I was not convinced at the beginning because I was thinking it was not applicable to my case. But at the end, I succeeded, and it was very efficient. So as I said, I practiced unit testing since now 15 years, roughly. 4 years with Scrum in not academia, but industry. Roughly, this is 17 projects, my own personal project, plus my professional one. In many languages, C++, C for the most part, a bit of Rust, Python, Node.js, Java when I was a student, and Go. And at the beginning, I was able to reach a code coverage, the number of lines covered by my test, which were 43%, and now I'm more to 90%, something like this. So I also seen the progress I had during this path. And I had 2 projects professionally where I was working with a team of 50 developers without unit tests. So it permits to feel how it's working, how we feel in front of the code with and without the unit test, and to see the difference. So before moving to the unit test itself, I will make a little bit of philosophy and motivation why we want to make unit tests. So you know probably the Manhattan project in 1945 at Hanford. They wanted to build some nuclear reactors. They wanted to build it fast, very quick because of the war. And of course, the problem of the pollution and the treatment of the waste were not the question at that time. So the waste, mostly, they put it in the sand in some big tanks, the liquids, the muds, everything, the radioactive stuff. And now we don't have the list of what is in these tanks. And 55 years later, so 2010, they started to leak. There is a nice report, a report which has been made a few years ago, which estimates the cost to clean up these sites. Now it's 300 to 600 billion dollars up to 2090. That's what we call technical debt. So don't laugh, because in computer science we don't do best. We have also technical debt in computer science. This is what I will discuss now. So there was some studies. I take here a very old one. I should update with a new one, but just to show the concept. Capers-Jones is one of the first engineers who questioned the fact how much it's costing to solve a bug during the development phase of a software. And he studied a lot of software. It was, I don't have the numbers here, but it was something like 10,000 projects over the world, industry, academia, military, etc. And his conclusion is that globally, most of the bugs were of course, happening during, were introduced during the first development phase of the project, of course. But mostly that the cost, what is interesting for me is a purple line, which is here, which is an exponential, which is the cost of fixing a bug over the phase of the development of the software. And of course, this is also exponential, which means that if you wait to solve a bug, if you do it during the development while you just make your function, the fix is quite easy. You remember your function, there is nothing using your function aside, so you don't have to change a lot of things. You fix it, it takes 10 minutes and it's done. Now let's think, for example, at CERN, we deploy a software, there is a bug. Now we need to discuss what is the problem. Yes, the problem is this function, but if we change this function, it impacts this one aside. Are you agree for the guys who maintain this other function that I change the behavior of mine and blah, 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 blah. You need to make on the loop probably 2, 3, 4 engineers, which start to increase the cost of fixing the bug. Plus then you need to make a new release, etc. Okay, so we quickly understand that at some point, the more we advance in the life of the software, the more it will cost to fix the bugs. So the question is how we can avoid, to not see the bugs during the development phase as much as possible. Just about technical debt also, you probably never looked on the number of lines which your operating system is running. If you take a full Linux environment, this is roughly 400 million lines of code. Operating system, all the programs, etc. Here I'm taking the Linux distribution, which is Gen 2, to get the number. And most are in compiled language. So already in compiled language, you have some checks, because the compiler made some checks, which is not the case for Python, for example. Then in Python, you make a refactoring. The function aside is not checked if they use the same API. So how to validate that? We will see. We can think a way of testing. So to think about this way of testing, we can take a problem in a kind of real life. We will be a car engineer. So yeah, I take my car to take the photo. We will think we are Renault. I have no action at Renault, sorry. It's just this is my car. And we want to build a car, and you will be the car engineer responsible of the gearbox. Okay? How you proceed? How you proceed? First solution, probably the way the first car in the world has been made. You build a car, you test some things, and you give the car to someone. And this guy prays that the car is running well, at least the gearbox. Probably if the car is built like this, you will not buy it, or at least you are not sure to arrive at Annecy for the conference, for the school. So you don't do that. In computer science, we don't do that. Okay, not so strict. We don't do that, clearly. But what we do more in computer science, this is manual testing most of the time. We take a gearbox, we build a car, and we say to the student who just arrived in April, take the key of the car, and now make a Grenoble-Marseille with the car, try to hear if there is some problems while you are running. If you want to test some stuff, you take a stethoscope and you try to hear if the gearbox is making some noise. Try to look at the road at the same time also, to not hit a car. And you can conclude that your car is running. This is better than making nothing, but clearly the method is a bit handmade, we can say. Let's say that in computer science already, we most of the time are a bit here. Huh? We make a software, we test some things by playing with the software, and we consider it's okay. So this is one of the methodology we tend to use, not for everything, but for many things we are doing day to day. So if we want to improve, we can do better things. We can do still manual testing, but in a controlled environment. Instead of going to Grenoble-Marseille, where I don't manage the weather, the road, how it is, etc., we can build a test circuit. So near to my company, I can have a test circuit. I just take the car, and on the test circuit, I do all the time the same stuff. Turning right, taking a round point, parking, etc. And I can make a list of the tests to perform. So I note on a paper, I need to test this, I need to test this, I need to test this. Again, I take the student, and every time the student is making the test plan, driving the car, while I'm taking my Coca-Cola. This is already a bit better, but still a methodology which is a bit painful to apply day to day. Also meaning by a software is never doing one thing, because a car I can accelerate, go front, go rear, go right, go left. I summarize a bit, but the car is quite easy to test compared to a software which can do a lot of things. So in my software, if I already want to make a list of everything I need to test, it will not be so easy. So next thing, I can automate. I take my car, I put some automation script. So this is automated script. In computer science, I put some cameras, some motors to turn the wheel, etc. So the car can run automatically on the circuit. This is the automated test. Okay. In computer science, most of the time, this is a shell script, a bash script which runs the application and checks some output. But the problem is that when the shell script is buggy, I mean, when there is a problem with the car finishes in the side of the road, and then we need to guess what has happened. Is it the problem of the gearbox? Is it the problem of the test which is wrong? Is it the problem of something else in the car? You don't know, and this is a bit like a go-go gadget, and you need to guess that the problem is coming from your part of the car. And in practice, this can be costly quickly, because in practice, it's quite easy to make the integration test like this automated, but then to debug it, it's quite often a larger cost day to day. So we can do better. This is unit testing. So unit testing this time, this is what we call a test bench in car engineering. So you can take only the gearbox. You take the gearbox out of the car. You put it in a wall. In a controlled situation, and you put some electric motor on it. So you don't have a gas motor which is making noise, which is hard to maintain. You put an electric motor, the gearbox attached to the wall, and so you can look at it also directly when it is running. Also hearing if it's making some noise. You can put some infrared camera aside because you have access to the gearbox instead of having it in the middle of the car. You can make some probes, everything, some microphones, and measure a lot of things to really validate that it's running well. Okay, this is what we call unit test. I take the component, I put it in a controlled environment with some probes, and I validate that it exists in a strict way how it is running. I can do the same in computer science. This is also a good thing because you can sell to your clients that you improve some metrics on your gearbox because you can measure it. Less noise, less vibrations, and etc. Not in one term. I will use in one terminology. I will use a bit later. This is the mocking, the kind of mock. Here I mock the motor. I put an electric motor instead of the gas one. So I'm making a mock in terms of unit test terminology. a factice motor. So notice here that there is a contiguous transition. I'm passing from one gear. I can test that one gear has all the teeth which are well done. Then I test 2 gears, if they are working well together. Then I test 4 gears, 5 gears, and all the gearbox. Okay? And then the gearbox in the car, which is the integration test for the gearbox. And when I'm testing the car fully, all the car, we tend to call this the end-to-end test, everything in place. Some people are making a kind of big gap between the end-to-end test and the unit test. Myself, I'm kind of prefer to see that as a contiguous transition. I have 1 component, 2 components, 4 components, and I'm growing the number of components I'm testing as long as I'm progressing in my testing. The tool can change because for the end-to-end test, we sometimes use different tools than for the unit test. But apart of that, the methodology is quite the same. So how it looks? Let's take an example for a particle. This is a unit test to validate a particle simulation for particle physicists, for example. The good thing with a unit test is that I'm launching the unit test, it's saying at the end that 2 tests has passed and it's green, so it's okay. And I don't want to have to read that the number printed by the program should be 10 minus blah, 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 or I don't know what. I don't have to remember the values, it's automated in the test. And it just say me, it has passed, it's true, it's okay. So here an example of a unit test in Python, because it's simpler than to write than in C or C++. What I made, yeah. We test the absolute value function, so a very simple function, okay? We can test that value, absolute value of 0 is 0, absolute value of 20 is 20. And I can say, what I said here, I forget. I made a mistake here, this should not be there. Let me correct this. I put the wrong test here. For the absolute value, normally, we should just check 20, and there is one which is missing, which is minus 20. So in practice, the thing is that when you write your unit test, you try to think in terms of corner cases. What are the corner cases of my function? And I try to test some of them, not all, because I will not test 1, 2, 3, 4, 5. There is no interest to do that. I will just test some values. You will notice that all the time in the unit test framework, we are using the assert keyword. We are making assertions. This function should return this value when I call it with this parameter. This is most of the time what is a unit test. We can do a bit more complex one for particle. For example, this is what we call in computer science, we take the turtle here, a turtle which can go forward or go backward. We can take a particle which can move a bit. So we create a particle. We assert that its position is 0 at the beginning, and we move it from 10 position and check at the end that it's 10. Very simple example. I admit that your program is a bit more complex than that, but for a starting point, this is okay. Then we can test 2 particles, how they collide. For example, sending 2 particles, one against the other. So we create 2 particles which go front to front. We check that it collides, that the collision has happened, and that the particles go back in the other way at the end. And I progress like this in all my, if I'm making some particle physics, I should progress like this to make all my simulation validation. Notice that your test should stay simple. If your tests are to become, to have 500 lines, it's too complex. So you need to find a way to express in a simple way what you want to express in your test, which means that you need to have a semantic in your code which permits to have tests. Because if you pass more time to write your tests than to write your code, you will be, you will pay a high price. Also think that when the test will fail, you will have to guess what the test is doing, because probably you write the test 10 years ago, and you have to come back to the test and to understand what it is doing. If it's simple, you read it, you understand quickly what it is doing, you can debug it. So this is one of the important things of unit test. The good points, if my particle is not implemented the right way, when my test is running, it's telling me it's not running, and it's giving me some hints on what is wrong in my test. It's saying, I'm waiting the value 1.5, minus 1.5, for example, here, and I have obtained 3.0. Normally, if you want to debug your function, you have enough information to know directly what is broken in your code, which is not the case with the integration test, which is saying the car is crashed. Okay? So I really want to have something in the unit test, which is I encoded in my test what I expect in terms of values. For a more real case example, this is one of the projects I was working on a long time ago. This was a project with 3,000 lines of 30,000 lines of codes, sorry, and it's validated here in 9 seconds. One of the good points of the unit test is 9 seconds to validate this. Because one unit test is very simple, so it's very fast to execute. This is what is interesting also with the unit test. You will see that when you make unit tests, at some point, you will need to mock exactly the problem of the car, of the gearbox. If you need to put a gas motor with the gearbox plus the accelerator of the front panel of the car with the accelerator and everything, quickly you will have all the car in your test, which is a problem. So at some point, if you have a complex object hierarchy, you will try to cut, to make a cut in the hierarchy, and to say that you will mock everything which is in bottom. Okay, create the electric motor instead of the real motor. This is what we call mocking, to replace some component in my test. Not to take out all the program all the time, otherwise it's an integration test with everything. So a mocking is what? In computer science, if you have a function to test which is calling one function and another one, which is complex, normally it's doing some very complex stuff. I will programmatically cut the link to this function at the runtime and put the mock in place from the test to replace the execution and using the mock in place of the real function. Most of the time in computer science, a mock, this is a function which returns directly the value it expects. Okay? I make no computation inside, nothing. I say my mock will return all the time 25.3. This is my electric motor, which is running all the time at the speed I want it runs. How it looks in Python. I create my particles. And when I'm speaking about particles, sometimes I make some statistics, the collision. Sometimes it crosses and it collides, sometimes it's not colliding. So most of the time in particle physics, you use some random functions inside your collision function. And how to make a unit test with a function which is not returning all the time the same thing. It's a problem. Here, what I can do is I can mock the random function and say the random function return all the time 0.75. Okay, this is what I do here with mock.patch random.range, return value 0.75. So all the time I know my random function for this execution will return this value. So I can predict the result which will arise after that. Okay, so mocking is important to simplify what you are testing. I had a friend at some point of mine during my PhD who was saying, yeah, but me, I'm making networking. So networking, I'm communicating with another process elsewhere, which is another machine, so I cannot do unit test. And I say myself, yeah, but no, you cannot. You can make unit test. Cut the network, mock it. Of course, you cannot validate the sending of the message on the cable, but this you don't care normally. It should work well. But you can validate the packing of your message, the depacking, to who you send, and everything of the semantic of your messages. This you can test. So by doing some mocking, you can test everything. And I list here some frameworks which are useful for making tests in Python, in C++, C, Bash, and Rust or Go. For most of those languages, you find both a test framework and a mocking framework. Some of those languages, like Rust and Go, directly have this kind of, at least for the test framework, have them natively in the language. Some others need a library to help you to implement the test. So normally I kind of convince you that it could be a good thing, but I convince you with some very simple example. The turtle example which I show is not the code you are writing day to day. The code you are writing day to day is far more complex, so you can say yourself, probably it will not be so simple to implement in the real life. And also, when you are working in a team, you need to motivate your team to also use the methodology. So I will here make some feedback in terms of human aspect, because this is in software engineering, and we have the codes plus the humans, and we need to take care of the humans also. And this is very important for the success of a project. So when you try to push integration tests in a team, most of the time, everyone agrees, yeah, we will validate what we are doing. This is very nice. How to do it already? Some questions. Most of the time during the discussion, the day after the discussion, there is someone in the team who came with a bash script. Yeah, I tried yesterday night. I made this automation with this bash script, and it's fine. And we go for that. Okay. The problem is it looks easy at the first look. The problem is that at some point it starts to cost. So for example, during my PhD, we had a project with 10,000 MPI tests, integration tests, because we were testing all the conditions, not unit tests. So we were making all the combinations to run. And the first day we added the test suite, because we didn't add it at the beginning, we had 5,000, half of the test suite failing. Most of the time for the same reason, but in terms of motivations, it was a bit hard. Half of the test is failing. And the problem is that it was taking 1 week to run, because we were making the car, running the car, destroying the car fully, and it was taking a long time. It was a bit depressing and very hard, so nobody was, not a lot of people were looking on the test suite. In the end, we fixed a lot of bugs thanks to this test suite, but it was with a high price in terms of management. We had mostly to hire one engineer to manage this test suite full time. I had another experience with that. I was in a Scrum team in industry, only integration test. Test suite 40 minutes. So you remember the unit test I was saying in the example before, it was 9 seconds. So already here the integration test, most of the time when you have integration test, this is half an hour or 1 hour. This is quite common. So already the example I was showing before with the 9 seconds is the exact same example than this one, but with unit test. So when I was developing, to validate my code, this was make test 9 seconds. Okay, something is broken. When you have the integration test only, you launch the test suite. This is broken. You launch the test suite to check if it's fixed. Okay, and your development process is a bit broken. Also, you have to maintain it, which most of the time poses some issues. For example, for us, we had to migrate the test environment at some point in a new one. Migrating from, it was Jenkins to GitHub. And it was a cost of 5 months dedicated just to migrate the test suite. Because the integration test is also most of the time more complex in terms of environment. Where for my unit tests in the new environment, it was 1 week to port everything. Just to say that in long term, with unit tests, we win some things. So let's push the unit test philosophy to the team. Already, it's a bit harder because people start to understand that you need to make some effort in your code. It will not happen automatically with a bash script in 5 minutes. We are slower at start when we are making unit tests because we need to do the test. And of course, slower at start in our modern world, it's something we don't accept too much. So it's in practice a bit hard to convince the people to do that. And it's very hard to introduce in an existing software which has not been designed to make the test. If you don't have the gearbox in a box, but some gears just like this in the car, it will be very hard to take it out to make the test. And there is some first common kill, even if the people accept to make the test. Most of the time, there is some sentence which start to rise up. Or this function is too hard to test. I will not test it. This one is calling too many other functions. This is hard to test because I don't want to mock. I will not test it. Or this one, it's so simple. I will. It's sure it's running well. I will not test it. Bad thing because most of the time it is the buggy one which is called by everyone. There is also this one. Oh la la! To make your unit test, you need to change this function. Please don't touch this function because it has been too hard to make it running. It's dirty, but we don't want to touch it anymore. Please don't touch this code. If you start to go there, you will test. You will unit test nothing. This is a quite common kill in an existing project. So let's came back to my first discovery of unit test. So there was a teacher like me saying, yeah, unit test, this is the best, this is very good, etc., etc. Turtle, unit test the turtle. I was not convinced, frankly, because I say myself, okay, I will lose my time because I know to write codes which is not buggy. I'm perfect as a developer. My code is running, so you see, I succeeded to make it without tests. It was hard to see how to make the test in practice, in real life, because my real program is not a turtle with two functions. It's making some complex stuff. How I test that without making a long program? And I was not seeing the benefit, because my program was already existing. I mean, the first time I made it on a program which I already wrote. And I had the impression to lose my time, clearly. But this was also the problem is that I passed, I don't know, 2 weeks to make only unit tests, which is not very motivating in practice. And we prefer to make new things in computer science. So it's like if some people were saying to me, yeah, if you make a marathon, you will be very well suited in your body and you will feel great after that. But me, I don't know how to make a marathon, so I go to start to make the marathon without briefing. Of course, after 5 minutes, I'm gone. This is because I don't have the right methodology. So in practice, if you want to use a unit test, you need some disciplines. There is some things to apply, some methodology to apply and to stick with. So first, there is some sentence to ban from your world. This is a POC. I will make it later for the test. If you do that, this is finished. The POC, you cannot test it anymore if it has not been fixed to be tested. For some reason, first, you will never do it later because you will have some other stuff to do. But a bit worse, your design will not permit it because you will not have things about the test. You will have, you want to move to some other stuff. Nobody is happy to make 4 weeks of testing. This is not true. And the worst thing, your boss has already sold it to a client. So now you need to debug it and go fast to sell it, to make it running well enough for your client. This is also true in research. In research, you have something running. Your director came to you, say, make a paper with that, go to the conference, and blah, 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 and you don't have the time to make the test. This is finished. And I will show you that in practice, if you do the test later, you already lost half of the benefits of the test. So this is more or less making them after a while, after the development, this is more or less losing more time. So the question is, what is the benefit of unit test? We can say it's validating the program. Okay, true. For me, this is 20% of the interest only. There is far more interest behind that. The first one, which is it forces you to make a design. You cannot unit test something which has no design. If it's a blob, your code, it will be very hard to validate it. For example, one example, it completely forbids you from using global variables. If you have global variables and you want to make unit test, you will quickly understand that it's a bad thing to make global variables. So already a good thing. It makes a specification of your code. You have some example for every function how to use it. It's a kind of documentation which is always in sync with the code. And the documentation, all the time, you write it. 10 years later, it has nothing to relate it to your code how it is. because nobody checked it and you don't update it every time. For the test, you are forced, because you execute the test all the time, to keep it synchronized with your code. So it's a kind of documentation and specification which is in sync. For the internal API, because most of the time you make documentation of your external API, but with the unit test, you document your internal one. If you want to refactor, who want to make a refactoring in a code which has no test? No one, because you will break something for sure and have no way to see it. If you have unit tests, you say, okay, I change something. If something is broken, I will see it. Not 100%, but probably 80% of the time, which is already a good progress compared to 0. New developer. When you have a new developer which arrives in your team, he makes a mistake in the code. You make a mistake in the code the first time you enter in your code. What happened? You don't see the bug. So you continue coding, you make a new mistake, you continue coding, you continue mistake, and then there is a bug, which is visible. Now you have 3 bugs to debug at the same time. It's far more time to debug this because you will understand how they are related, the 3 together, instead of having 1. If I have unit tests, when I broke something, probably one test will tell me immediately that I broke something, and I have only 1 problem to fix. Okay? And it's not 2 months later that I need to remember what I did 2 months before. Remember that the new developer, this is you in 6 months. You in 6 months, you forget what you did, so you are always new in your code. So take care of yourself, as we can say. It also partly removes the funnel effect. And you know, when you have a feature to do, you do the first function, the second function, the third function, etc. And you progress like this for probably 4 months, because it takes 4 months to make your feature. During 4 months, you are not sure that what you are doing is valid, probably, because you have no way to validate. No way. Very few ways to validate what you are doing. If you are making your unit test, it stops a bit this effect, because all the time you say, this part of the code, I made it, I validate. This part of the code is made, it's validated. This part of the code is validated, etc. So you are always sure that your code is running well. It's not saying that you are going in the right direction, but at least you know that there is no big bug in your program. So when you make everything together at the end, in 4 months, you are more lucky. There is more luck that everything is running well from the first try. And in your head, frankly, when you have the habit to work with unit tests and you came back to the methodology without, you feel it in your head. It's some stress which are there because you need to ensure. If you don't have the unit test, this is you by your head that ensures that everything is going in the right direction. With unit test, you delegate a bit your stress to the tests themselves. Not all, but partly. Safety for the QA guy. Quality assurance. So it depends. In research, we don't have too much this kind of people who check the quality of a software, but in companies we have. Every time in a team, you have some people who are more exigent about the quality of the software. Not everyone has the same kind of feeling about that, but there is always one in a team which has a bit more than the others. And the problem is that if there is no metrics to measure where we are in terms of quality, there can be some very hard discussion because one is feeling the software is going in a poor way, where the others is thinking that it's okay. Me, I'm more in the case, I'm exigent, so most of the time I'm one of the guys who is saying, hey, we need to improve a bit the thing. If I can come with the list of tests which are broken, saying that 20% of the tests are broken by what we did the last month, we have some numbers to discuss. And this is a bit easier to have the discussion in practice. A teacher. If you don't know how to make, when you are a new developer, or a new developer in a new domain, because we are always new developer in our life in computer science, you don't know too much what are the design patterns which are useful for the case you are doing, the first time you are doing this domain. Either you discuss with someone who explains you what are the design patterns, Either by doing the unit test, you get some feedback. Because if you write some code and you cannot write the unit test because your code is too complex, it's telling you directly, immediately that you make a wrong design. So you can improve your design now. Or say, next time I will think differently, but I know by feedback that I'm in the wrong way. So it's a kind of feedback also you have by yourself in front of your computer without waiting someone to come to you to say, yeah, but what did you did in your design? This is a poor design. You get it by yourself immediately with your test. And this is something very useful to progress and to improve yourself in terms of design. It avoids to make gas machine. Why? So let's think about the morning not kiss function. The morning you take your coffee, you go to take the dog out and to open the garage to take your car. If you are a good computer scientist, normally you split everything in one class or function separately. But you will see that for optimizations, here we'll discuss optimization. Sometimes you want to go a bit faster, and you can say probably in the function where I'm making the coffee, I'm also taking the leash on my back and putting the key in my pocket. So I'm ready for the next stage to do it. Okay? Not a problem in terms of code. I can mix everything in the same function, and it's okay. Probably it can run. Now, if I want to make the unit test, I will see the problem immediately, because to test the garage, I will need to call the coffee function. So it will tell me that I make a mistake. Of course, the good point normally is to probably to call the leash and the key during the coffee, but having them in some separated functions. So I can test them separately and use them separately everywhere. Okay? The thing is that with the test, I'm seeing it directly when I'm making the code immediately. So I will improve my software and avoid to make a gas machine with something which are melted the one in the others. Facing the entropy. When you are making a code, during the life of the code, if you make a code for 10 years, the code is growing, and the complexity of the code is growing, of course. And this is more an exponential than something linear. The more you add, the more it's complex, and the slower you are over time to progress in your code. If you want to reduce the complexity of your code, you need to make some refactoring sometimes. Because something which were not planned, start to make the code a bit melted. If you refactor, you can make it in a better shape. But if you don't have unit test, you will wait a long time before making refactoring, because you will risk to break your code. If you have unit tests, you can make some refactoring, mostly every month, probably, and keep the complexity of your software not perfect, but a bit lower. So in practice, you will still have an increase of the complexity, but a bit slower compared to the fact of doing zero refactoring. Notice that if you are not doing refactoring, at some point you need some heroes, because when your software becomes too complex, there is always something which happens in a team, that there is one hero which succeeds to understand this complexity, where the others is not capable. Take more time to understand this complexity. And it's not good to have an hero in a team, because then you go faster in front, alone, and all the others are swimming to follow the project. Question sur Discord. Discord question. What is a unit? A function, a method, a branch in a method. What is a unit? For me, a unit is something which is small enough to be tested. I don't consider, we can consider, strictly speaking, a function, one function, one unit. For me, this is too small. I would say a class. A class is a good unit. And on this class, we can test several properties on the function we have inside this class. It can be, if the classes are very simple, a set of class, 2, 3, 4 class. For me, this is what is a unit. Okay, below that, if you start to have 20 class, 40 functions, this is not anymore a unit for me. So about refactoring, the way I'm working now, thanks to the unit test, when I have a new feature to do, I know I want to do this feature, and probably my code needs some reshaping before making the feature. And this is like when you want to make some work on a road, you need to prepare this work. Same thing for the software engineering. I'm making some refactoring before to prepare my work, testing to validate that everything is good. Sometimes I made the refactoring in 2 steps because one should be too big in one go. And then I make my feature, and then I test. Okay? So this is my way to work. Refactoring, feature, refactoring, feature, refactoring, feature. And so I keep my, my code in a better shape. If you have with integration test, this is a daily dev coffee flow, which I call. With integration test, the test which is taking 40 minutes, you code for 5 minutes. You run your test for 40 minutes. You debug for 20 minutes. Of course, during the 40 minutes of test, you can take a coffee. You test again after the debugging for 40 minutes. Probably take again a coffee. And you do that a long time. Okay? Not very efficient. So, of course, if you do that, your boss will come to you and to say, maybe you should work a bit more efficiently. So, in practice, the more realistic case is you code for 5 minutes, you code for 5 minutes, you code for 5 minutes, you code for 5 minutes for 2 days, and then you make your test. Then, of course, you have now 10 bugs which are there. So you pass 4 days to debug, and where you take 1 coffee at the beginning, at the end, this is a bit stressful, and then this is coffee to find the bug, because now the client is waiting you for having the product. With the unit test, 5 minutes of coding, 10 seconds to test, 10 minutes to debug, probably, because I make something complex, 10 seconds to test, etc. And in my process, when I'm coding, change one line, testing, change one line, testing, change one line, testing, change one line, testing. And like this, every time I'm introducing a bug, I'm kind of seeing it with a 5-minute delay, I see the bug. And so I'm far more efficient like this to make my development. Also, when I cut at the end of the day, when I leave, I know that what I did is working. So I leave my head free. For the previous case, if you code for 2 days, for the day before, when you leave, I remember I have this problem, I need to think tomorrow where I am, I know this is buggy this, and you feel it in practice in your body. Of course, you can take coffee also with the test, more for a good reason. Where is your knowledge? You have some code. Is the code the knowledge of your domain? Who think it's the code with the knowledge? If I need to redo a version 2, what I will recall? The code to know what to do, or something else? The specification, yeah. My own knowledge, my experience, personally, what I have in my head. So there is a specification which is official, and there is the one which is my experience when I made the version 1, which is probably in the head of 3 developers. One has left, so I lose it. The 2 others are still there, but they forgot part of the thing. So in practice, one of the important knowledge when you want to redo a new version of the software is the knowledge of the corner cases, the one which has posed you some problems the first time. If you remember this, you will do your new version faster than the previous one. So in practice, what I'm saying is that most of the interest to remember if you want to make a version 2, it's not too much the code, also the code, yes, but first the corner cases. And this is exactly what is encoded in the unit test. In the unit test, I encoded all my corner cases, so if I want to have a new version, I can do it quite easily because I have the list of corner cases. Can give an example. I was developing a memory allocator during my PhD. The original version written in C, so I was discovering the domain, and so compare the numbers with some back focus, not directly the number for the number. The original C version, it was 1 year of development. I retranslated it in C++ at some point, 1 month. and I retranslated it in Rust at some point, 2.5 weeks. Thanks to the unit test, because, so don't take the 1 year, because 1 year I was discovering, making my research, okay? But to rewrite memory allocators is something very hard. Huh? If you have a bug in a memory allocator, you pass for every bug 1 week, 2 weeks to debug it, okay? So thanks to the unit test, I was able to get the Rust version running quite quickly, because every bug I was making, the unit test I had in the previous version in C or C++ was telling me that I made a mistake in the new version in Rust. So you encode like this your knowledge. So if you want to make a new version, you can do it quite efficiently to make some exploration in new languages. In terms of ecology, the test suite has its lights, because you don't need some network connection, you don't need some specific hardware, or not too much. You can test all the functions locally on your laptop. Me, I was CERN, I was developing for the I/O system of LHCb, which was supposed to run on 500 servers. And I don't want it to test everything on 500 servers all day to day, because it was a waste of resources. So I was making everything in my unit test, testing all my communications, network, protocols, etc. in unit test. This I can do on my laptop. And sometimes I was going to the production system to make my scaling test, not wasting the resources all the time. So a laptop is enough to develop an application for cluster. You don't need the cluster all the time to debug it, which if you don't have unit test, this is every time you have a bug, you go to the cluster and pass running, debugging, running on the cluster all the time on probably, I don't know, say 64 cores or more. In terms of CI, if you have a cycle of a minute or 9 seconds, for the 9 seconds I had, if you had the compile time, it's 1 minute most of the time in the continuous integration system. 1 minute to run, one server is enough for the full laboratory. Okay. Now, if you have 40 minutes of integration test for everyone in the team, now you need 2, 3 servers for the whole laboratory to run it. More resources wasted. So I don't want to say not doing integration test. I want to say that as the integration test costs more, I will do some, because of course I need to validate the car on the road. Otherwise, there is no meaning to buy the car. But I will do less. I will do more unit tests and less integration tests, some, to validate what I'm doing. So I kind of optimizing the price of validating my software. So I have a kind of test density which is increasing, many unit tests, and the more I'm going to the integration side, I'm doing less tests like this to have just some to validate some properties globally. Just a word in research, because this is a domain we tend to think that it's useful for companies because they need to make something working. But in research, you have tons of ideas, and you want to change your path every 3 months. I mean, 3 months, probably a bit less, but it's quite common to say, I have a new idea to make my stuff, so I will bifurcate in my research. If you have a Python code, for example, and you want to change your path, good luck to ensure that everything is running well. If you have unit tests, it will be a bit faster to change your idea, to change something and test new ideas. You want to explore many things, so it's a bit like the train station. You can explore more ideas if you are efficient to test them. So in research, I would say this is probably far more important than in industry, because in research, you don't want to lose your time in debugging. This is not your goal in your life. Okay. Where in industry, this is your goal to have something running, strictly speaking. So you use the unit tests to get the validation in industry. In research, you get it to get flexibility in your code. The flexibility to test many things. And me, I have seen it during my research, because the fact that I was using unit testing everything, I was able to test all my runtime system on large-scale applications. Because I was developing, for example, things about memory management. If you have a buggy memory management, of course, you cannot test a 1 million line application, because it will fail, and you will pass, as I was saying at the beginning, 2 months to debug. So of course, you will say 2 months for the PhD, it's gone. I will not do it. So you will just waste some ideas just because you were not able to implement it. If you are able to have something running, you can test on real scale systems and get more research. I probably let you the impression that with that I will lose some time. Okay, I will give you an example, a real life example. So as I was saying, I was working a few years ago on LHCb, one of the big detectors at CERN, to make the I/O system. So we wanted to build an I/O system to be able to transport 40 terabits per second. Sorry, a lot of data. Which arrived with 10,000 optical fibers going from the detector in the subsurface of the LHC and going up to the surface, and then 500 servers in front to get the data. A kind of a nice challenge. Also because if this I/O system is not working, you have 500 physicists who has no data to work with. When I arrived at CERN, there was an engineer who made the first version of the prototype for this software to handle the data transport, which I tried to recompute the development time for the different steps. So in red. So here I tried to rebuild the time myself by looking the Git log. So take those numbers a bit like roughly numbers, not exact one. I was discussing with the developer to check that it was what he estimated also, but it's looking back. So for the core development, it took 5 months without unit test. No unit test in this software. LibFabrics, this is a network driver. It was 3 months myself to make the implementation in the project. TCP, it was 5 months. Infiniment verbs, which is a very hard network to program, 11 months by a student which was knowing well Infiniment. And OmniPath, 5 months by me. And we can see the numbers in red. So in red, the core development has took 3 months. I already had a version 1, so of course I win some time on the core development. It's probably the same for both in reality. But for LibFabric, 1 month to get the driver. Of course, because I have unit tests, so every time I had a bug with my LibFabric network part, I was validating on my laptop, which was far easier than debugging on a cluster with 2 servers communicating together. So I win here a factor 3, roughly. TCP, this is interesting because the version 1 has been made by a network expert, so it was 5 months. And you see that here the green version is 4 months, so not a big win, but by a student who has no expertise in C or C++. So you see also that with the unit test, you can also have some less experts people in your team which come to collaborate with you without too much problems. Also because to help him, when he was brokening something in my code, there was some test saying that it's broken, and I was able to help him very efficiently. So I was kind of letting him making the things and learning by himself, even if he was not knowing the domain by himself. So in terms of human, we win also. Here, not in time, but in terms of human. And for the Infiniment verbs, it was the version 1 was made by a student who made an Infiniment simulator before, the one who was knowing well what Infiniment is. And the version 2 again was made by a student working, coming to collaborate with us for a few weeks, and which was not knowing nor MPI nor RDMA, remote direct memory access, which is the technology which is used by Infiniment. So no knowledge about this kind of network, and was able to make the driver in 0.5 months. Sorry. So in about 2 weeks. So we see that clearly at the end we are winning on time for the development. Okay, on time in terms of human also. Of course, at the beginning I'm losing a bit. Let's say for the first 2-3 months you are losing in your development, but then you accelerate after that. The student also came to us to make the failure recovery of the code, because when one node was disconnecting, we needed to make the reconnection automatically, which is something very hard to do in Infiniment, and he was making it because I prepared the work with a model in terms of simulation with the unit test before his arrival. He made it in 1 month. For someone knowing MPI and the failure recovery in MPI, 1 month, this is very short for Infinimount. So let's conclude here. Of course, the win you will have, I will give some rules about the timings. Of course, it depends on the languages, your objective, your status about unit test, where you are with this technology. Myself, I allow myself to code for 2-3 weeks without making the test to make a prototype. This I allow myself. Then after 2 weeks or 3 weeks, I stop myself, I make the test, and then I continue. If my project has some interest to go for months or years. If you go for a project which you know from the start it will go for a few months, make your unit test from the beginning. This is simpler. For the first 2 months, roughly 2-3 months, you will be slower. So you will have to accept that for 2 months you lose a bit your time, but then you accelerate after that. In terms of coverage, the number of lines which are validated by your test, what is the good thing? In Python, you can say, as it's a language which is done in a way you don't have too much errors to manage, you can say that 90% of coverage is quite good already. In C and C++, it will be harder to reach such coverage because there is more errors, more if and else statements to manage the errors, and you will not be able to pass to everyone by your test. 80% is already a nice target. Don't try to get 100%, this is useless. I have seen one project, I was one time in a project, me who is complaining about unit test not being there. This project was saying, you should have 99% of coverage. Let me say that this is the wrong thing, because then you pass more time to make some tests which are useless than to code. And for winning, no security in the end. What I really want in practice is not too much the coverage by itself, but to have at least one test per function or class. Okay? Because if I have one test per function or class, it means that if I have an example to test each function, if I need to extend my test later, I already have some templates to extend them. And I also validated the API. Now I said my main interest on unit test is validating the API. So if I have one test per function, it's enough to validate the API. I don't need 3 or 4 of them. This is not useful. To learn in an existing software, because most of the time you have an existing software when you start unit test. Don't start with the top function because they will be very hard to test because they depend on too many things. Try to start with the bottom one. The bottom one, you can probably find some function which depend on nothing. Really try to make the test for those one. It's a good start to learn by yourself. And later you will see if you can go up and see the others. So let's conclude here for this presentation. Always compare what you are doing in software engineering with real-world engineering, because sometimes we make something which has no meaning in computer science because it's virtual. And it's not because it's virtual, it has no cost. We have seen it with the integration test, which is costly. In research, you want to explore algorithms, so you don't want to lose your time in debugging. So this is interesting also for research this domain. And in terms of human aspects, I was a bit fast here. There is also some other interest I did not discuss here. There is a lot of interest about unit tests about the human aspect in the team. The dynamic of the team is quite different if you have unit tests than if you don't have. I have, seen it in real life. There is a lot of things which rise up when you have them. So be patient and look the dragon in the eyes. Of course, the first time you will make unit tests, you will not be good to make them. Accept it and try to progress time to time. For me, it took me at least 2 to 3 years to be able to be very efficient on everything in unit test. And you will improve yourself by learning the ways to test different stuff, which when you do the first time something, you don't know how to much express your test on this domain. You need to learn this over time. I don't know where I am in terms of time. And if there is some questions. Yes, there is some questions on Discord. Is it possible to test? Oh, no. Is it somehow possible to test was the code vectorized or if it's mid or not? Yes and no. There is some tools like Macao who permit to extract some metrics about vectorization and etc. You can integrate that on unit test, but I would say this is not a good idea to make it. But strictly speaking, you can in a very hard way. There was some other questions. Slides will be available at the end of the presentation. Yes. Unit test script URL. Unit test. I don't understand the question about the unit test script URL. Sorry, Victor. And this is all for the thing I have to say now. And I should stop because we are late. Yeah, there are some questions. Where is the microphone?
You said people don't want to write unit tests because it takes time. Do you think AI can be a game changer for this? And do you have any experience of writing unit tests assisted with AI?
If some people are happy to write unit tests? Or?
No, if AI can help writing unit tests faster.
Yes, yes. So question of point of view. Yes, the AI can do it now quite efficiently in practice. Myself, I try myself to not use too much AI for coding, so I will not be the best to answer this question. My answer to this question would be, if you should do something with the AI part, I will make the implementation and make the test yourself. Because what you want to validate with the test is not to check that your code is correct, but your API is correct. For this, you have to look at it and to play with it. If you skip this from your hand by saying the AI will do it for you, it will validate the code for the validity, but not for the API semantic. So myself, this is what I'm saying. For me, I really understood after time to time that the greatest interest of unit tests is not the validity of the code, even if it is also, but the API validity.
So have you ever worked in a test-driven development where you write tests before your code?
So before, yeah, there's a nice, this is a nice question, so I repeat a bit. TDD, test-driven development, the idea is I write my test and then I write my code. I write my test, then I write my code, so the specification is done before the coding. Myself, I never used it. I mean, I tried sometimes. I found it very inefficient because I lose a lot of time to write. Also because in C++, this is not very easy to do, because in C++, if your function is not there, you have a seg fault. In Java or something like this, where this TDD thing has been developed, you get an exception when the code is not running and the tests are continuing to pass. So in C++ already, this is very hard to do. And even if you do that, I would say one function, making the test of one function and making the function directly, for me, it's okay. I do it sometimes. Most of the time, I do the reverse. I do one function, one test, one function, one test. There is some people doing also the totally TDD thing, which is I make all the tests of my program. For example, there is some virtual machines which has been developed like this, like Parrot. The virtual machine Parrot has been developed like this. They made all the specification with unit test and says, now we make the implementation. It's very interesting in terms of validity, but the problem is that when you are making the implementation, of course, you will discover that you miss some things during the test, which cannot be done that way. So then you have to change your design and do again your test to adapt to them. So you pay the price twice, which is costly. Now, if you are making a plane, this is probably a very good idea. If you are making a program for a researcher, I would say this is about, a lose of time. Yeah.
So one point, I think when it comes to C++ or C coverage, I think if you sort of modify the meaning of coverage to, because you mentioned like do not include, or like you have a lot of throws, right? Or exceptions. Like if you strip away the exceptions, which you can do with some programs like LCOV, I think that you should have 90–95% of coverage.
Yeah. So the problem is that there is no tools to remove the exceptions from the numbering. So in practice, when you use some tools to make the code coverage measurement, you always have the code coverage measurement about all the code exceptions considered. So yes, if you consider that you don't check the errors, reaching 95%, 90% is okay in C++. The only problem is that there is more errors to handle in practice in this language.
So my main question has to do with randomization. So for me, randomized unit tests are extremely important. But so then you get, I mean, your runtime gets quite a lot higher. I've never written a project where my tests run for just 10 seconds.
So there is a great thing here. I will not pass too much time to discuss it, but I have some slides I did not discuss here because I don't have time. I made it in a longer presentation where it is. Yeah. Mutable testing. This is probably exactly, I mean, coming back to what you were saying. This is a bit of a theoretical topic because I never seen some people really applying it in production except for a bit some toy things. The question is your test enough to validate all your code? So one way is to say, I will mutate my program, so introduce some mistake, making a minus instead of a plus, and checking if one of the tests is failing to see it. So this is what they call mutable testing, is to mutate the program and to see if at least one test is seeing the mistake. If it's not the case, I need to add some tests to validate my stuff. Randomizing the values of the test, yes and no, because the problem is that if you are using some random values, when the test will fail, you will be in difficulty to understand what the test has made. And one of the goals of the unit test is that when the test fails, it helps you quickly to understand what is happening.
But not if your unit test is small enough, right? Like
if it's very small, yes, of course. But then remember again, for me, the goal of unit test is what I learned after the usage. It is to validate the API. So having tons of unit tests saying for absolute value, for example, I can test 1, 2, 3, 4, 5, -1, -3, it takes a long time, but for which gain in practice, not a big one. So me, I prefer to have something I understand in my values. Yeah, but true that in certain cases, it's probably interesting.
Thank you.
For example, if you work on schedulers, different scheduling, to generate some different schedulings, this can be interesting to generate them randomly and check that everything is valid in all the cases. Yes. Any other questions? Or in the lab, in the Discord? So yeah, they are saying that there is some talk on CPPCon 2026, which we are covering the question about the AI and the unit testing. If someone want to look at it, you can go to look on that.
Or maybe you can improvise a bit with what's in the reading desk under your PC.
De quoi? Yeah, I forget you put it here. Yeah, normally we make the joke during the presentation. What do you think is a simpler thing to test? The one on the left or the one on the right? One is as components, so probably it depends. I don't know exactly what these electronic cards are doing, so probably this one is simpler in terms of what it is doing. But in terms of components, this one is better designed because I can extract the component and unit test them. Okay. So make components in your code. This is also why I'm thinking that unit test is really related to object programming. The object programming is making the component by design. So you will see quickly that in C, if you program in C where there is no object programming by default, if you want to make unit test, you will make some kind of object programming in C by default. Thanks for the reminder. We can stop here, maybe. Everyone tired? Thanks everyone for this day. Pierre, you want to say something?
Yeah, just to close the day properly. So thank you everyone for joining us today. So we'll start again tomorrow at 9 a.m. normally with Wizardry in C++ and CPU computing, and then we'll finish with blocking and with profiling at the end of the day. So maybe, yeah. So thanks for attending the school, and see you tomorrow for next stuff. So thank you for all satellite sites. We saw also your comment and your photos in the chat. So it was a pleasure to have. So continue to follow the school and to send us if you have questions, remarks, or even just nice photos on your site. And hopefully you're doing well. And we'll do that again tomorrow. So see you tomorrow.